Welcome back. Tonight, we settle in with the gentle mathematics of stellar death, as we follow Subrahmanyan Chandrasekhar on his long sea voyage from India to England in 1930, where a young man of 19, armed with little more than a notebook and the quiet hours of an ocean crossing, calculated the precise mass at which a dying star could no longer support itself against collapse, a limit that would bear his name, though recognition, like starlight from distant sources, would take decades to arrive. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. On the 19th of October, in the year 1910, in the city of Lahore, which then lay within the Punjab region of British India, a child was born who would one day reshape humanity's understanding of how stars live and how they die. The child was given the name Subrahmanyan Chandrasekhar, though in time he would come to be known simply as Chandra to his friends and colleagues, and the circumstances of his birth were, in many ways, unremarkable for a family of his standing and tradition, yet they contained within them the seeds of something quietly extraordinary. Lahore in those days was a city of considerable administrative importance, a place where the machinery of the British colonial government turned with steady regularity, and it was here that the Chandrasekhar family had settled, following the professional postings that shaped the lives of so many educated Indian families during that era of railway expansion and bureaucratic growth across the subcontinent. The father of young Subrahmanyan was a man named Chandrasekhar Subrahmanyan Iyer, and he held the position of Deputy Auditor General of the Northwestern Railways, a role that carried with it both responsibility and a certain measure of prestige within the colonial administrative structure. This was steady, methodical work, the kind of employment that required precision and attention to detail, the careful examination of figures and accounts, the quiet maintenance of order within the vast network of railways that stretched across the northern reaches of India. Yet to describe Chandrasekhar Subrahmanyan Iyer solely in terms of his professional duties would be to miss something essential about the man, for he was also a person of considerable artistic accomplishment, particularly in the realm of Carnatic music, that ancient and intricate classical tradition of southern India. He was an accomplished violinist, skilled in the complex ragas and talas that form the foundation of Carnatic performance, and music filled the household in ways both formal and informal, woven into the fabric of daily life alongside the more practical concerns of railway auditing and family management. But the father's talents extended even further, into the realm of letters and translation, for he undertook the challenging work of bringing the plays of Henrik Ibsen, the Norwegian dramatist whose works had transformed European theatre, into the Tamil language. This was no small endeavour, requiring not only fluency in both languages but also a deep sensitivity to the cultural and emotional nuances that give literature its power, and the fact that a railway auditor in British India would devote his intellectual energies to such a project tells us something important about the atmosphere of this household, where the life of the mind was valued alongside the practical necessities of earning a living and raising a large family. The mother of young Subrahmanyan was named Sitalakshmi, and she too was a person of remarkable intellectual depth, though her formal education had been limited in the manner that was common for women of her generation and background. Despite these constraints, which might have discouraged a less determined spirit, Sitalakshmi possessed a keen intelligence and a love of learning that found expression in various ways throughout her life. Most notably, she too engaged with the works of Ibsen, translating his play A Doll's House into Tamil, a work that seems particularly resonant given its themes of women's independence and the constraints of social expectation. that both parents should have been drawn to the same foreign dramatist, each working independently to render his challenging works into their native tongue, speaks to a shared intellectual life between them, a mutual respect for ideas and for the transformative power of literature that would have permeated the atmosphere of the home in which young Subrahmanyan spent his earliest years. Subrahmanyan was the third of what would eventually be 10 children, 4 sons and 6 daughters, a large family even by the standards of the time, and the household must have been a busy place, filled with the sounds and activities of children at various stages of growth and development. In such a setting, one might imagine that individual attention would be difficult to come by. Yet the evidence suggests that the Chandrasekhar parents were deeply committed to the education and intellectual development of all their children, creating an environment in which curiosity was encouraged, and learning was treated not as a burden but as a natural and pleasurable part of life. The rhythm of such a household, with its daily routines of meals and studies and play, with its seasonal observances and family gatherings, would have provided young Subrahmanyan with his first understanding of how the world is ordered, how patterns repeat and vary, how complexity can emerge from simple underlying structures. The family belonged to the Tamil Brahmin community, with ancestral roots reaching back to the Tanjavur district in the southern reaches of India, that region of temples and rice fields and ancient learning that had long been a center of Hindu scholarship and artistic achievement. The Brahmin tradition placed enormous emphasis on education and intellectual attainment, and families like the Chandrasekhars carried this heritage with them even as they moved to distant cities in pursuit of professional opportunities. Tamil itself is one of the oldest continuously spoken languages in the world, with a literary tradition stretching back more than 2,000 years. And to grow up in a Tamil-speaking household was to be immersed in a culture that valued language and learning with particular intensity. The stories and poems of that tradition, the philosophical texts and religious hymns, would have formed part of the background of young Subrahmanyan's childhood, even as his parents engaged with the very different literary traditions of 19th century Europe. Among the extended family connections that would prove significant was an uncle named Chandrasekhar Venkata Raman, known more commonly as C.V. Raman, who was the elder brother of Subrahmanyan's father. At the time of young Subrahmanyan's birth, C.V. Raman was himself engaged in scientific work that would eventually bring him international recognition, though this lay still some years in the future. In 1930, when Subrahmanyan was a young man of 19, his uncle would be awarded the Nobel Prize in Physics for his discovery of what came to be known as the Raman effect, a phenomenon involving the scattering of light that has found applications in countless areas of scientific research. The presence of such a figure within the family circle, even at some remove, would have helped to establish science as a legitimate and even prestigious pursuit, demonstrating to the young Subrahmanyan that an Indian could achieve recognition at the very highest levels of international scientific achievement. The early years of Subrahmanyan's childhood were spent in the railway quarters that came with his father's position, those practical and often standardized accommodations that the colonial administration provided for its employees and their families. Life in railway quarters had a particular character, shaped by the comings and goings of trains, by the rhythms of a transportation network that connected distant cities and brought news and goods and people from far-off places. For a child, there might have been something fascinating about this proximity to the great engines of travel and commerce, the sense of being connected to a larger world beyond the immediate surroundings of home and neighborhood. The railways themselves were, in their way, monuments to the power of applied science and engineering, vast systems that depended on precise calculations of time and distance, on the careful management of schedules and resources, and growing up in such an environment might have instilled an early appreciation for the practical applications of mathematical and scientific thinking. Within the household itself, the influence of the mother, Sita Lakshmi, appears to have been particularly important in nurturing young Subrahmanyan's love of learning. Mothers in traditional Indian households often served as the primary educators of young children, overseeing their early lessons and instilling in them the habits of study and reflection that would serve them throughout their lives. That Sita Lakshmi herself was a woman who had pursued intellectual interests despite limited formal education would have sent a powerful message to her children about the value of self-directed learning, about the possibility of expanding one's mind through determined effort rather than relying solely on institutional instruction. The young Subrahmanyan would have observed his mother reading and writing, would have seen her engaged in the demanding work of literary translation, and these observations would have shaped his own understanding of what a life devoted to intellectual pursuits might look like. The atmosphere of the Chandrasekhar household seems to have been one in which intellectual ambition coexisted comfortably with traditional Tamil values, where the pursuit of knowledge was understood not as a departure from cultural heritage but as an expression of it. The family observed the customs and practices of their community, maintained connections with relatives and with the broader network of Tamil Brahmin families, and yet they were also open to influences from beyond this immediate circle, as evidenced by their engagement with European literature and their participation in the modern institutions of colonial India. This combination of tradition and openness, of rootedness and curiosity, would have provided young Subrahmanyan with a secure foundation from which to explore the wider world of ideas, giving him both a sense of identity and the confidence to venture beyond familiar boundaries. As the years of early childhood passed, the family began to consider the question of education with increasing seriousness, for in a household that valued learning so highly, the choice of schools and the quality of instruction available were matters of considerable importance. Lahore, for all its administrative significance, may not have offered the educational opportunities that the Chandrasekhars sought for their children, and like many families of their background and aspirations, they began to look toward the great cities of southern India, where Tamil culture flourished and where institutions of higher learning had been established. Madras, the city that would later be known as Chennai, was the natural destination for such a family, a metropolis that served as the cultural and educational capital of Tamil-speaking India, home to colleges and schools and libraries that could provide the foundation for serious academic achievement. And so, around the year 1918, when young Subrahmanyan was approximately 8 years old, the family made the significant decision to relocate from Lahore to Madras, a journey that took them from the northwestern reaches of the subcontinent to its southeastern coast, from the Punjab to Tamil Nadu, from a city where they had lived as transplants to a region where their cultural and linguistic roots lay deep in the soil. This move would mark the end of the Lahore period of Subrahmanyan's life and the beginning of a new chapter in Madras, where his formal education would begin in earnest and where the intellectual gifts that his parents had nurtured would find fuller expression. The railway that his father had helped to administer would have carried them on this journey, the same great network of tracks and stations and locomotives that connected the far-flung regions of British India, and one can imagine the family settling into their compartment for the long journey south, the children looking out at the changing landscape, the parents contemplating the opportunities and challenges that awaited them in their new home. The years in Lahore had been formative ones, establishing the foundations of character and outlook that would shape Subrahmanyan throughout his life. He had been born into a family that valued knowledge and achievement, that maintained deep connections to Tamil cultural traditions while remaining open to the wider world of ideas, that included among its members individuals of genuine intellectual distinction. He had spent his earliest years in an environment where music and literature were woven into daily life, where both parents demonstrated through their own example the rewards of intellectual engagement. These influences would remain with him as he grew, informing his approach to his studies and eventually to his scientific work, providing him with a sense of purpose and a standard of excellence that would guide him through the decades of research that lay ahead. But all of that was still in the future, and for now, the young boy from Lahore was simply beginning the next stage of his journey, moving with his family toward the city that would become his home and toward the educational opportunities that would set him on the path to becoming one of the 20th century's most distinguished scientists. In the year 1910, a young couple named Chandrasekhar Subrahmanyan and Sita Balakrishnan welcomed their first son into the world in the city of Lahore, which at that time was part of British India and situated in the Punjab region, far to the northwest of the Tamil-speaking lands from which both parents had originally come. The father worked as an officer in the Indian Audited Account Service, a position that required the family to move according to the dictates of the colonial administration. And so the early years of the boy they called Chandra were spent in various postings across the subcontinent. But it was not until 1918, when young Chandra was approaching his 8th birthday, that the family finally settled in a more permanent fashion in the city of Madras, the great coastal metropolis of South India, where the Bay of Bengal stretches out toward the eastern horizon and the humid air carries the scent of jasmine and salt. The house on Edward Elliot's Road became the center of the Chandrasekhar family's life for many years to come, a substantial residence befitting a senior government official and his growing household. The street itself was lined with similar homes belonging to families of comparable standing, shaded by tamarind trees and neem trees that offered some respite from the intense southern sun, and the neighborhood represented a quiet enclave of professional and educated Tamil Brahmin families who valued learning and achievement above most other virtues. Here the children would grow up surrounded by books and conversation about ideas, by visitors who discussed literature and science and music, and by the gentle but persistent expectation that intellectual accomplishment was not merely desirable but was in some fundamental way the purpose of a fortunate life. Young Chandra did not attend a regular school during his early childhood years, a circumstance that might seem unusual but was not entirely uncommon among families of his background and means during that period. Instead, he received his primary education at home, where his parents and a succession of private tutors guided him through the fundamentals of learning in an unhurried and thorough manner. His father, Chandrasekhar Subrahmanyan, took a particularly active role in this instruction, and it was from him that the boy first learned the elegant structures of mathematics, beginning with arithmetic and progressing steadily through more advanced topics as the child's aptitude became increasingly apparent. The father also taught English, which was essential for any Indian hoping to advance in academic or professional life under British rule, and Tamil, the ancient and beautiful language of their ancestors, with its rich literary tradition stretching back more than 2,000 years. This home education continued until Chandra was approximately 12 years old, and during these formative years he developed habits of mind and patterns of study that would remain with him throughout his entire life. There was no rushing through material simply to cover it, no anxiety about keeping pace with other children in a classroom setting, but rather a methodical and patient approach to understanding each concept fully before moving on to the next. The tutors who came to the house on Edward Elliot's Road found in their young pupil a remarkable combination of quick comprehension and genuine curiosity, a child who not only learned what he was taught, but who wanted to know why things were so and what lay beyond the boundaries of each lesson. The household was also rich in books, and young Chandra developed the habit of reading widely and deeply from an early age. Among the volumes that captured his imagination were popular science books that explained the workings of the natural world in terms accessible to a curious young mind. And it was through these accessible texts that he first encountered the great questions of physics and astronomy that would eventually become his life's work. The behavior of light, the nature of the stars, the vast distances between celestial objects, the mathematical laws that seem to govern everything from falling apples to orbiting planets. All of these topics kindled in him a fascination that burned steadily rather than brightly, a persistent and growing interest rather than a fleeting enthusiasm. When Chandra was around 12 years of age, the time came for him to enter formal schooling, and his parents enrolled him at Hindu High School in the Triplicane neighborhood of Madras. Triplicane was and remains one of the oldest areas of the city, centered around an ancient temple dedicated to Lord Vishnu, and the high school there had a reputation for academic rigor and for producing students who went on to distinguished careers in various fields. The transition from homeschooling to a classroom full of other boys might have been difficult for some children, but young Chandra adapted readily, and it quickly became apparent to his teachers that this new student possessed abilities in mathematics that were quite extraordinary for his age. His performance in mathematics was not merely good or even excellent, but was of the sort that causes teachers to take special notice and to remember a student for many years afterward. The problems that challenged his classmates he would solve with an ease that seemed almost casual, and yet there was nothing boastful or showy in his manner, only a quiet confidence in working through logical steps to arrive at correct conclusions. The other subjects held his attention as well, and he was a diligent and successful student across the curriculum, but it was in mathematics that his gifts were most apparent, and it was mathematics that increasingly occupied his thoughts during those formative years at Hindu High School. During his teenage years at the school, Chandra began to read more advanced scientific literature, including the published research papers of Chandrasekhar Venkataraman, the brilliant Indian physicist who was conducting groundbreaking work on the scattering of light at the University of Calcutta. It is worth noting that C.V. Raman was in fact related to the Chandrasekhar family, being the younger brother of Chandra's father, which is to say that this internationally recognized scientist was the boy's paternal uncle. Reading the papers of a relative who was actively pushing forward the boundaries of human knowledge must have had a profound effect on the young student, demonstrating in the most concrete and personal way possible that scientific research at the highest level was not something done only by distant figures in foreign lands, but was a path that an Indian, and indeed a member of his own family, could successfully pursue. The papers themselves were technical and demanding, dealing with topics in optics and the behavior of light that required substantial mathematical sophistication to fully understand. But Chandra worked through them with determination, building his comprehension piece by piece and returning to difficult passages until their meaning became clear. This early exposure to primary research literature, to the actual documents in which scientists communicated their discoveries to one another, was an important part of his intellectual formation, teaching him not only about the specific physics involved, but also about the form and rigor expected in professional scientific work. He was learning, without perhaps fully realizing it at the time, how to think like a physicist and how to evaluate claims and evidence with a critical but open mind. Alongside his growing interest in physics, Chandra also encountered during these years the first of the classical physics textbooks that would shape his formal understanding of the field. These texts, many of them written by European authors and used in universities across the world, presented physics as a systematic and mathematically precise discipline, a body of knowledge accumulated over centuries and organized according to logical principles. Working through such books required patience and concentration, and Chandra developed both qualities in abundance, spending long hours in study and building a foundation of knowledge that would later support his own original contributions to science. Another influence that touched him deeply during his adolescence was the story of Srinivasa Ramanujan, the self-taught mathematical genius from Tamil Nadu who had, just a few years earlier, astonished the mathematical world with his extraordinary discoveries. Ramanujan had grown up in modest circumstances in the town of Kumbakonam, not far from Madras, and had taught himself advanced mathematics from whatever books he could obtain, eventually corresponding with the famous British mathematician G. H. Hardy and travelling to Cambridge to collaborate on problems of number theory and analysis. The story was well known throughout educated Tamil society and was a source of considerable pride, for here was one of their own who had been recognized by the greatest mathematicians in the world as possessing a mind of rare and wonderful power. For young Chandra, the example of Ramanujan was both inspiring and in some ways sobering. Both were Tamil Brahmins, both had shown mathematical ability from an early age, and both came from families that valued learning and intellectual achievement. But Ramanujan's life had been tragically short, for he had died in 1920 at the age of only 32, his health broken by illness and the difficulties he had faced in England. The lesson that Chandra drew from this story was not merely that mathematical greatness was possible for someone of his background, though that lesson was certainly important, but also perhaps that such gifts carried with them a serious responsibility, and that a life devoted to mathematics or science was not merely a career but something closer to a calling that demanded everything one had to give. Within the Chandrasekhar household, there were clear expectations regarding academic excellence, expectations that were communicated not so much through stern lectures or overt pressure as through the general atmosphere of the home and the examples set by the adults. The father had achieved a respected position through his own efforts and abilities, and the Uncle C. V. Raman was demonstrating what heights an Indian scientist could reach through brilliance and hard work. The children understood from an early age that education was valuable, that knowledge was to be pursued diligently, and that success in intellectual endeavors was perhaps the highest form of success to which one could aspire. It is also important to note, and Chandra himself would later remark upon this with a certain thoughtful sadness, that the educational opportunities available to the children in the family were not distributed equally between the boys and the girls. His sisters, however intelligent and capable they may have been, faced limitations and barriers that their brothers did not, for the social conventions of the time and place meant that advanced education and professional careers were much more accessible to young men than to young women. Chandra noticed this disparity, and while as a child and adolescent he could do little to change the circumstances of his society, the observation seems to have stayed with him, a recognition of the arbitrary nature of certain advantages and disadvantages, and perhaps a seed of the fairness and openness that would characterize his later dealings with students and colleagues from all backgrounds. As the years at Hindu high school passed, Chandra's habits of study became ever more rigorous and systematic, patterns of intellectual discipline that would characterize his entire career in science. He learned to read slowly and carefully, to take thorough notes, to revisit difficult material until it was fully mastered, and to connect new knowledge with what he had already learned rather than treating each subject as isolated from all the others. These habits may sound unremarkable when described in such plain terms, but in practice they represented an approach to learning that was unusually mature and effective, an approach that would later enable him to master multiple areas of astrophysics in succession and to produce original research of lasting importance over a career spanning more than 6 decades. By the time he completed his studies at Hindu high school, Chandra had laid the groundwork for everything that was to follow. He had a solid foundation in mathematics and the beginnings of a deep knowledge of physics. He had been exposed to the example of great scientists both in his own family and in the broader Tamil scientific tradition. He had developed work habits that would sustain him through the most demanding intellectual challenges, and he had come to understand that a life devoted to the pursuit of understanding the physical universe was the life he wished to live. The boy who had learned his first lessons from his father and tutors in the house on Edward Elliot's Road was now ready to enter the next phase of his education, to study at university and to begin his journey toward the discoveries that would eventually earn him a place among the most important astrophysicists of the 20th century. But all of that lay in the future, and for now we may simply rest with the image of a teenage boy in Madras, reading physics books in the quiet hours, working through problems with pencil and paper, and dreaming perhaps of stars. In the year 1925, at the age of 15, Subrahmanyan Chandrasekhar passed through the gates of Presidency College in Madras to begin his undergraduate studies, and in doing so he entered an institution that had long served as one of the most distinguished centres of higher learning in all of India. The college stood in the heart of the city, its buildings arranged around courtyards where students gathered between lectures, and the atmosphere within its walls was one of serious scholarly pursuit combined with the particular energy that comes when young minds first encounter the great questions of their chosen fields. Chandrasekhar had arrived there having already demonstrated considerable mathematical ability during his earlier schooling, and he enrolled in the program that would lead to a Bachelor of Arts degree with honours in physics, a course of study that would occupy him for the next 5 years and would prove to be foundational in ways that perhaps even he could not have fully anticipated at such a young age. The faculty at Presidency College during those years included several figures who would leave lasting impressions upon their students, and among them was Prasanta Chandra Mahalanobis, a statistician of growing reputation who taught physics at the college and who brought to his lectures a certain rigor of thought that the young Chandrasekhar found deeply appealing. Mahalanobis was himself a man of wide-ranging intellectual interests, someone who understood that the boundaries between disciplines were often more permeable than institutional structures might suggest, and his presence on the faculty meant that students at Presidency College were exposed to ways of thinking that extended beyond the conventional physics curriculum. There were other teachers as well, each contributing in their own manner to the education of the students who passed through their classrooms, and together they created an environment in which a young person of exceptional ability might begin to discover the shape of their own intellectual ambitions. It was during these undergraduate years that Chandrasekhar developed the habit of reading deeply and systematically in the scientific literature, a practice that would remain with him throughout his entire career and that distinguished him even among his highly accomplished peers. One text in particular captured his attention during this period, and that was Arnold Sommerfeld's treatise entitled Atomic Structure and Spectral Lines, a work that represented one of the most comprehensive and mathematically sophisticated treatments of atomic physics available at that time. Sommerfeld was a German theoretical physicist of immense standing, a teacher who had trained many of the leading figures in the emerging field of quantum mechanics, and his book was not an easy one, filled as it was with detailed mathematical derivations and the careful working through of physical principles to their logical conclusions. The young Chandrasekhar read this text with an intensity that went beyond what was required for his coursework, studying it page by page with the kind of concentration that allows knowledge to become not merely memorized but truly understood, absorbed into the very structure of one's thinking. This deep engagement with Sommerfeld's work was characteristic of the approach that Chandrasekhar would take to his studies throughout his time at Presidency College, an approach marked by a preference for going directly to the most authoritative and challenging sources rather than relying upon simplified summaries or secondary accounts. He seemed to understand, even at that young age, that real mastery of a subject requires grappling with it in its full complexity, and he had the patience and the mathematical preparation necessary to undertake such grappling successfully. The hours spent with atomic structure and spectral lines were hours of genuine intellectual labor, the kind of concentrated effort that builds the foundations upon which later achievements can be constructed, and they left him with a thorough grounding in the physics of atoms and the quantum mechanical principles that govern their behavior. The depth of his reading and the quality of his understanding soon manifested themselves in a remarkable way, for at the age of 18, while still an undergraduate student, Chandrasekhar wrote his first scientific paper, a theoretical treatment of Compton's scattering that demonstrated both his command of the relevant physics and his ability to contribute original work to the scientific literature. Compton's scattering, named after the American physicist Arthur Holly Compton, refers to the phenomenon whereby X-rays or gamma rays change their wavelength when they scatter off electrons, a process that had been crucial in establishing the particle-like properties of electromagnetic radiation, and that continued to be a subject of active theoretical investigation during the 1920s. The young Chandrasekhar's paper addressed certain aspects of this phenomenon with a clarity and sophistication that belied his years, and when it was submitted for publication, it was accepted by the Proceedings of the Royal Society, one of the most prestigious scientific journals in the world. The publication of this first paper in such a distinguished venue was an achievement of no small significance, and it announced to the broader scientific community that a young physicist of considerable promise was emerging from India. To have work accepted by the Proceedings of the Royal Society while still an undergraduate was unusual by any standard, and it reflected not only the quality of Chandrasekhar's scientific thinking but also a certain boldness of ambition, a willingness to believe that his ideas might be worthy of the attention of established scientists in Europe and beyond. This confidence was not the product of arrogance but rather of a clear-eyed assessment of his own abilities combined with the conviction that good scientific work should be judged on its merits regardless of the circumstances of its author. The publication of his paper led to correspondence with Arnold Sommerfeld himself, an exchange that must have been gratifying for the young student who had spent so many hours studying the German physicist's textbook. Sommerfeld was known for being generous with his time in corresponding with young scientists who showed promise, and he was evidently impressed by what he saw in Chandrasekhar's work, responding to the young man's letters with encouragement and engagement. This correspondence represented Chandrasekhar's first direct contact with the international community of theoretical physicists, a community that operated largely through the exchange of letters and papers across national boundaries, and it gave him a sense of connection to the larger world of scientific inquiry that existed beyond the walls of Presidency College. Another crucial influence during these undergraduate years came in the form of a scientific paper rather than a textbook, specifically a 1926 publication by the British physicist Ralph Fowler concerning the behavior of matter under conditions of extreme density. Fowler's paper addressed the question of what happens to matter when it is compressed to the extraordinary densities found in certain types of stars, and it made use of the newly developed principles of quantum mechanics to explain how electrons in such matter would behave. This work caught Chandrasekhar's attention and would prove to be of decisive importance in shaping the direction of his later research, though at the time he encountered it, he could not have known just how central these questions would become to his scientific career. The paper planted a seed that would germinate over the following years, introducing him to problems at the intersection of quantum physics and stellar structure that would eventually lead to his most celebrated contributions to astrophysics. During his time at Presidency College, Chandrasekhar also had the opportunity to meet and interact with Chandrasekhar Venkataraman, who was then working at the Indian Association for the Cultivation of Science in Calcutta, and who would win the Nobel Prize in Physics in 1930 for his discovery of the scattering phenomenon that bears his name. Raman was a towering figure in Indian science, a man of tremendous energy and confidence who had demonstrated that world-class experimental physics could be conducted in India, and his encouragement of the young Chandrasekhar's theoretical interests was meaningful during these formative years. Raman recognized in the young student a kindred spirit, someone with the intellectual capacity and the drive to make significant contributions to physics, and he supported Chandrasekhar's ambitions even as he himself pursued a very different style of scientific work. The relationship between these two would later become more complicated, marked by tensions and disagreements that sometimes characterize interactions between strong personalities. But during the Presidency College years, Raman's influence was largely positive and encouraging. As Chandrasekhar progressed through his undergraduate studies, it became increasingly clear that he would need to pursue advanced training abroad if he wished to develop his abilities to their fullest extent. And to this end, he applied for and received a Government of India scholarship that would support his studies at Cambridge University in England. This scholarship was a significant achievement, recognizing his status as one of the most promising young scholars in the country, and it opened the door to an education at one of the world's leading centers of scientific research. The prospect of studying at Cambridge, where so many of the physicists whose work he had been reading actually lived and worked, must have been tremendously exciting, and it represented both an opportunity and a validation of everything he had accomplished during his years at Presidency College. The summer of 1930, the period immediately before his departure for England, was a time of particularly intense intellectual activity for the young Chandrasekhar. He devoted himself to a careful study of Ralph Fowler's work on white dwarf stars, those peculiar stellar objects that represent the final stage in the evolution of stars like our Sun, collapsed remnants with masses comparable to the Sun but sizes comparable to the Earth, and therefore with densities millions of times greater than ordinary matter. Fowler's application of quantum mechanical principles to understand the internal structure of these objects had opened up a new field of investigation, and Chandrasekhar immersed himself in this material with the same thoroughness that he had previously brought to his study of Sommerfeld's textbook on atomic physics. This summer reading would prove to be of momentous importance, for it was during the sea voyage from India to England later that year that Chandrasekhar would make the theoretical breakthrough concerning white dwarf stars that would eventually bring him lasting fame. When Chandrasekhar completed his studies at Presidency College, he did so with the highest honors, a formal recognition of the exceptional quality of his academic work over the preceding 5 years. His record at the college had been one of consistent excellence, marked by the publication of his first scientific papers, by his correspondence with leading physicists abroad, and by the depth and range of his reading in the scientific literature. He had entered the college as a talented 15-year-old with a gift for mathematics, and he was leaving it as a young physicist of demonstrated ability and considerable ambition, ready to take his place among the students at Cambridge and to continue developing the ideas that had begun to take shape during his undergraduate years. By the time of his graduation, Chandrasekhar had made a decision that would shape the entire trajectory of his scientific career, choosing to focus his future research on problems of stellar physics rather than continuing in the field of atomic physics that had occupied much of his attention during his undergraduate studies. This decision reflected his growing fascination with the questions raised by Fowler's work on dense stellar matter, and his sense that this area offered opportunities for fundamental contributions that might suit his particular talents and interests. The choice was in some ways a bold one, for atomic physics was then at the very center of excitement in theoretical physics, with the new quantum mechanics transforming understanding of matter at the atomic scale, while stellar physics might have seemed to some a less glamorous field. But Chandrasekhar followed his own intellectual instincts, recognizing that the problems of stellar structure pose profound questions about the behavior of matter under extreme conditions, questions that would require precisely the combination of mathematical skill and physical insight that he possessed. Throughout his years at Presidency College, the young Chandrasekhar had displayed a confidence in his own abilities that was notable even among his gifted peers, a quiet certainty that he was capable of making significant contributions to physics, and that his ideas deserved to be taken seriously by the international scientific community. This confidence was not mere youthful bravado, but rather the product of his demonstrated success in mastering difficult material and in producing original work that met the standards of the most demanding scientific journals. His intellectual ambition was evident in the scope of his reading, in his willingness to correspond directly with eminent physicists abroad, and in his determination to pursue the most challenging problems he could find. As he prepared to leave India for Cambridge in the autumn of 1930, Chandrasekhar carried with him not only his scholarship and his letters of introduction, but also this essential quality of mind, this conviction that he had something valuable to contribute to the great ongoing project of understanding the physical universe. And so the chapter of his life that had begun as a 15-year-old entering Presidency College drew to a close, giving way to the next phase of his education and the remarkable discoveries that awaited him in the years to come. In the summer of 1930, a young man of 19 years prepared to leave India for the first time in his life, and the journey he was about to undertake would carry him not only across the Arabian Sea and through the Suez Canal to the distant shores of England, but also, quite unexpectedly, to the edge of an idea that would eventually reshape our understanding of how stars live and how they die. Subrahmanyan Chandrasekhar, known to his family and friends as Chandra, had been awarded a Government of India scholarship to pursue graduate studies at the University of Cambridge, and in late July of that year he boarded a steamer of the Lloyd Tristano shipping line in the port of Bombay, carrying with him a modest collection of luggage, a considerable measure of youthful ambition, and several books of theoretical physics that he intended to study during the long passage ahead. The ship would take 19 days to reach Venice, traveling westward across the Arabian Sea, northward through the Red Sea, and then through the Suez Canal into the Mediterranean, and Chandra had decided that he would use this time productively, as young scholars often do when they find themselves with uninterrupted hours and no competing obligations. Among the books he had packed were works by Arthur Eddington, the eminent British astrophysicist whose popular writings had first inspired Chandra's interest in the physics of stars, and also a paper by Ralph Howard Fowler, a theoretical physicist at Cambridge who had recently published an important analysis of the dense matter found inside white dwarf stars. There was also material by Arnold Sommerfeld, the German physicist whose work on quantum mechanics and atomic structure had helped to establish the modern understanding of how matter behaves at very small scales, and Chandra intended to work through these texts carefully, preparing himself for the advanced studies that awaited him in England. The sea voyage itself was, in many respects, entirely ordinary, with the ship making steady progress through calm waters and the days passing in the gentle rhythm of shipboard life. And yet something quite extraordinary was taking place in the mind of this young passenger, as he sat with his books and papers in whatever quiet corner he could find. Chandra had become deeply interested in the problem of stellar structure, which is to say the question of how stars maintain their shape and stability against the tremendous force of their own gravity, and he was particularly curious about white dwarf stars, those peculiar objects that astronomers had discovered to be extraordinarily dense, packing roughly the mass of our Sun into a volume no larger than the Earth. The existence of such dense matter posed a puzzle for physicists, because ordinary matter, the kind we encounter in our daily lives, resists compression quite firmly, And yet white dwarfs seem to have overcome this resistance somehow, achieving densities millions of times greater than anything found on Earth. Fowler had proposed a solution to this puzzle in 1926, drawing upon the newly developed quantum mechanics to explain how matter could exist in such a compressed state. The key insight involved something called Fermi-Dirac statistics, which describes the behavior of a particular class of particles known as fermions, and electrons, the tiny negatively charged particles that orbit atomic nuclei, belong to this class. When matter is compressed to extreme densities, the electrons are forced into ever closer proximity with one another, and according to a principle discovered by Wolfgang Pauli, no two electrons can occupy exactly the same quantum state at the same time. This means that as you squeeze electrons together, they are forced into higher and higher energy states, because the lower energy states become fully occupied and no further electrons can fit into them. And this creates a form of pressure known as electron degeneracy pressure that resists further compression. Fowler had shown that this degeneracy pressure could explain how white dwarfs support themselves against gravity, and his analysis seemed to provide a satisfying account of these strange stars. But Chandra, sitting aboard that ship in the summer heat, found himself wondering whether Fowler's analysis was complete. The electrons inside a white dwarf, compressed to such extraordinary densities, would be moving at tremendous velocities as they occupied those high energy states, and Chandra began to consider what would happen if those velocities approached the speed of light. When particles move at speeds comparable to the speed of light, the ordinary rules of Newtonian mechanics no longer apply with sufficient accuracy, and one must instead use the special theory of relativity that Einstein had developed at the beginning of the century. Fowler's analysis had treated the electrons using classical, non-relativistic mechanics, which is perfectly adequate when the particles are moving slowly. But Chandra suspected that for the most compressed white dwarfs, with the highest densities, the electrons might be moving fast enough that relativistic effects would become important. And so, as the ship made its way across the Arabian Sea, the young scholar set about combining the principles of special relativity with Fermi-Dirac statistics, working through the mathematics of what is called a relativistic degenerate electron gas. The calculations were intricate but not impossibly so, requiring careful attention to how the relationship between energy and momentum changes when particles move at relativistic speeds, and Chandra worked steadily through the details, writing out his equations in a notebook as the ship rocked gently beneath him. The mathematics led him to an expression for the pressure of the electron gas that differed significantly from Fowler's non-relativistic result, and when he examined the implications of this new expression for the structure of white dwarfs, he found something quite unexpected. In Fowler's analysis, the degeneracy pressure always increased rapidly enough as the star was compressed to balance the inward pull of gravity, no matter how massive the star might be. This meant that white dwarfs of any mass could, in principle, exist in stable equilibrium, supported against gravitational collapse by the quantum mechanical repulsion of their electrons. But Chandra's relativistic calculation told a different story. When the electrons are moving at speeds close to the speed of light, the relationship between pressure and density changes in a subtle but crucial way, and the degeneracy pressure no longer increases quite as rapidly with compression as it does in the non-relativistic case. This seemingly small modification has profound consequences, because it means that for sufficiently massive stars, the degeneracy pressure cannot increase fast enough to counterbalance the ever-growing gravitational force, and there exists a maximum mass beyond which no stable white dwarf configuration is possible. Chandra worked out the value of this maximum mass, performing the calculations with the tools available to a 19-year-old theoretical physicist traveling by sea, and he found that it corresponded to approximately 1 4/10 solar masses, which is to say roughly 40% more than the mass of our Sun. This number, which would eventually become known as the Chandrasekhar limit, represented a fundamental boundary in the physics of stellar evolution, though Chandra himself did not yet fully appreciate just how revolutionary his finding was. Below this limit, a star that exhausted its nuclear fuel could settle into a stable white dwarf configuration, slowly cooling over billions of years but otherwise unchanging. But above this limit, something else must happen, because the physics simply does not permit a stable degenerate configuration, and the star faces what Chandra would later describe as gravitational catastrophe. The implications were startling, though Chandra approached them with the measured caution of a young scientist who was not entirely certain whether his calculations were correct or whether he might have made some error along the way. If a massive star could not become a white dwarf, then what would become of it at the end of its life? The matter would continue to collapse under its own gravity, with no known force capable of halting the compression, and this seemed to lead toward physical conditions so extreme that they challenged the understanding of physics in 1930. Chandra did not attempt to answer this question fully during his voyage, recognizing that he was already venturing into territory where the established physics provided limited guidance, but he understood that he had identified something important, a limit that nature imposed on the possible configurations of stellar matter. The ship continued its journey through the Red Sea and into the Suez Canal, passing through the narrow waterway that connected Asia to Europe, and then emerged into the Mediterranean for the final leg of the voyage to Venice. Throughout these days, Chandra refined his calculations, checking his work and considering the assumptions he had made, and by the time the ship docked in Italy in mid-August, he had assembled a reasonably complete analysis of the relativistic degenerate electron gas and its implications for white dwarf structure. He was excited by what he had found, with the particular kind of excitement that comes from discovering something genuinely new, from seeing a pattern in nature that no one else has noticed before. But his excitement was tempered by uncertainty about how his findings would be received, and whether his analysis might contain some subtle flaw that more experienced physicists would identify. From Venice, Chandra traveled by train across Europe to England, arriving in Cambridge to begin his studies at Trinity College under the supervision of Fowler himself, whose paper had inspired the work on the ship. The young man from India carried with him not only his notebooks and his luggage but also this extraordinary result, worked out during those 19 days at sea, and he began to share his findings with the astronomers and physicists he encountered. His presentation of these ideas was modest and tentative, as one might expect from a student newly arrived in a foreign country and uncertain of his standing among established scholars, and he did not initially trumpet his discovery as a revolutionary advance. He was, after all, contradicting certain implications of the work done by Fowler, his own supervisor, and he was aware that bold claims from unknown students are often met with skepticism, however well-founded those claims might be. In the months that followed, Chandra wrote up his results in a more formal manner and submitted a paper to the Astrophysical Journal, which was published in 1931, presenting the calculation of the limiting mass for white dwarfs. The paper was received with interest but also with some confusion, because its implications were so different from what the astrophysical community had previously assumed about the fate of stars. The existence of a maximum mass for white dwarfs meant that the story of stellar evolution could not end the same way for all stars, that nature must have different plans for the most massive objects, and this was a complication that many astronomers were not yet prepared to accept. But the calculation itself was sound, the mathematics correct, and the physics well-grounded in established principles. And over time, despite considerable resistance, the result would eventually be recognized as one of the most important discoveries in 20th century astrophysics. And so we may picture this young man, not yet 20 years old, sitting aboard a ship on a long sea voyage, working steadily through his calculations as the waters of the Arabian Sea passed beneath the hull, and arriving at an insight that would shape our understanding of the universe for generations to come. The voyage was quiet and unhurried, the days passing one after another in the gentle rhythm of travel, and the discovery was made not in a great observatory or a famous laboratory, but in the modest surroundings of a passenger ship, with nothing more than books, paper, and a keen mathematical mind. It was a beginning, though Chandra did not yet know how far this beginning would eventually lead, and the number he calculated, approximately 1.44 solar masses, would come to bear his name, a permanent marker of that summer journey from Bombay to Venice in the year 1930. In the autumn of 1930, a young man of 19 years arrived at the grey stone courtyards of Trinity College, Cambridge, carrying with him a small trunk of belongings and a notebook filled with calculations that would eventually reshape our understanding of how stars die. Subrahmanyan Chandrasekhar had journeyed from the warm shores of Madras across thousands of miles of ocean, and now he found himself in a place of ancient traditions, of scholars in flowing black gowns, of chapel bells marking the slow passage of hours, and of long evenings when the English damps settled into everything and the light faded early through leaded windows. He had come to pursue doctoral studies under the supervision of Ralph Howard Fowler, a physicist of considerable reputation who had himself made important contributions to the statistical mechanics of dense matter, and who would prove to be a thoughtful and supportive guide through the intricacies of academic life at one of the world's most venerable institutions of learning. The Cambridge that Chandrasekhar entered was a place of extraordinary intellectual ferment, though you would not necessarily have known it from the quiet quadrangles and the unhurried pace of afternoon tea. In the Cavendish Laboratory, Ernest Rutherford presided over experiments that were probing the very heart of the atom, and in the mathematics faculty, some of the finest minds in theoretical physics were working through the implications of the new quantum mechanics that had transformed the discipline in the preceding decade. Among these figures was Paul Adrien Maurice Dirac, a man of legendary quietness and precision, whose lectures on quantum mechanics Chandrasekhar attended with great attentiveness, and from which he gained a deeper appreciation of the mathematical structures underlying the behavior of matter at its most fundamental level. Dirac was not given to unnecessary words or social pleasantries, and his lectures were delivered in a spare and economical style that some found difficult to follow. But Chandrasekhar recognized in this approach a kind of austere beauty, a commitment to clarity and rigor that he found deeply congenial to his own temperament. The work that occupied Chandrasekhar during these early Cambridge years was a natural continuation of the calculations he had begun aboard the ship from India, though now he had access to better libraries, more knowledgeable colleagues, and the quiet encouragement of Fowler, who recognized that his young student had stumbled upon something of genuine significance. The question at hand concerned the ultimate fate of stars, and in particular those collapsed remnants known as white dwarfs, which represented the final state of stars like our own Sun after they had exhausted their nuclear fuel and contracted under the relentless inward pull of their own gravity. Fowler had shown, using the principles of quantum statistical mechanics, that such stars could be supported against further collapse by a phenomenon called electron degeneracy pressure, which arises from the Pauli exclusion principle and prevents electrons from being squeezed indefinitely close together. But Chandrasekhar had realized, during that long voyage across the Arabian Sea, that when the electrons in such a star are moving at speeds approaching the speed of light, the usual formula for this pressure must be modified to account for the effects of special relativity, and this modification has profound consequences for the maximum mass that a white dwarf can possess. Through patient and meticulous calculation, working through lengthy derivations in the libraries and common rooms of Trinity College, Chandrasekhar refined his earlier estimates and developed what he called the exact relativistic degeneracy formula, which gave a precise mathematical description of how the pressure in a white dwarf varies with density when the electrons are moving at relativistic speeds. The result of these calculations was striking in its clarity: the existence of an upper limit to the mass of a white dwarf star, above which no amount of electron degeneracy pressure could prevent the star from collapsing further under its own weight. This limiting mass, which we now call the Chandrasekhar limit, is approximately 1.4 times the mass of our Sun, though the precise value depends somewhat on the chemical composition of the stellar material, and it represents one of the fundamental constants of stellar astrophysics, a number that nature has fixed and that determines the ultimate destiny of countless stars throughout the universe. Below this limit, a dying star can settle peacefully into the white dwarf state and cool gradually over billions of years. But above this limit, something else must happen. Some other fate must await, though what that fate might be was not yet clear in the early 1930s. The years at Cambridge passed in this way, filled with calculations and lectures and the slow accumulation of understanding. And in 1933, two significant events marked Chandrasekhar's growing stature in the academic world. He was awarded his doctoral degree, the formal recognition of his years of study and research, and he was elected to a fellowship at Trinity College, a position of considerable prestige that provided him with rooms in the college, meals at high table, and the freedom to pursue his research without the distractions of teaching duties or financial worry. To be a Fellow of Trinity at such a young age was a remarkable achievement, and it reflected the high regard in which his work was held by those who understood its significance. He was now a member of that ancient community of scholars, with all the privileges and responsibilities that entailed, and he continued to refine and extend his calculations on white dwarf stars, preparing to present his findings to the wider astronomical community. The occasion for this presentation came on the 11th of January, 1935, at a meeting of the Royal Astronomical Society in London. The Royal Astronomical Society was the premier organisation for astronomers in Britain, a venerable body that had been founded more than a century earlier and whose meetings were attended by the leading figures in the field. And Chandrasekhar had been invited to present his work on the mass limit of white dwarf stars to this distinguished gathering. He prepared his talk with characteristic care, setting out the physical assumptions, the mathematical derivations, and the conclusions that followed from them with clarity and precision, and he delivered his presentation to an audience that included many of the most eminent astronomers of the day. The mathematics were sound. The physics was well grounded in the established principles of quantum mechanics and special relativity, and the conclusions seemed inescapable. There exists a maximum mass for white dwarf stars, and stars above this mass cannot end their lives in the white dwarf state. What happened next would remain with Chandrasekhar for the rest of his life, though he rarely spoke of it and maintained throughout a dignified restraint that reflected both his personal character and his deep commitment to the ideals of scientific discourse. Immediately following Chandrasekhar's presentation, Arthur Stanley Eddington rose to speak. Eddington was at that time the most famous astronomer in the English-speaking world, a man whose popular books had brought the wonders of the universe to millions of readers, and whose scientific work on stellar structure and the theory of relativity had earned him international renown. He had been instrumental in organizing the eclipse expedition that had confirmed Einstein's prediction of the bending of starlight, and his voice carried enormous weight in the astronomical community. When Eddington spoke, people listened, and what Eddington said on that January afternoon was devastating in its dismissiveness and its apparent authority. Eddington declared that he did not believe Chandrasekhar's result, not because he had found an error in the mathematics, but because he found the conclusion philosophically unacceptable. He called the idea that stars above a certain mass would be unable to reach a stable final state a form of stellar buffoonery, a reductio ad absurdum that showed not that nature behaved in such a way, but that there must be some law of physics preventing such an outcome. He spoke with the confidence of a man who had spent decades thinking about the internal structure of stars, and he invoked his prestige and his rhetorical skill to suggest that Chandrasekhar, despite his evident mathematical ability, had somehow gone astray, had followed his equations to a conclusion that nature would never permit. The audience, faced with a disagreement between an unknown young Indian physicist and the great Eddington, naturally deferred to the established authority, and Chandrasekhar found his work dismissed, not refuted on scientific grounds but simply set aside as implausible. The effect of Eddington's intervention was profound and long-lasting. Potential supporters who might have spoken up for Chandrasekhar's work remained silent, unwilling to challenge the most famous astronomer in Britain on a matter that seemed to touch on deep questions about the nature of stellar evolution. The astronomical community, by and large, followed Eddington's lead and treated the question of the white dwarf mass limit as unsettled at best and probably mistaken. Chandrasekhar found himself in the painful position of being unable to convince his colleagues of a result that he knew to be correct, watching as his careful calculations were brushed aside by a wave of authoritative dismissal. It was a humiliating experience, made more so by the public nature of the disagreement and the clear implication that he, a young man from the colonies, had overreached himself in challenging the established understanding of stellar physics. And yet, privately, a different picture was emerging. Among the physicists who understood the underlying mathematics and the principles of quantum mechanics and special relativity on which Chandrasekhar's work was based, there was no doubt that his calculations were correct. Niels Bohr, the great Danish physicist who had revolutionized our understanding of atomic structure, expressed his support for Chandrasekhar's result in private conversations. Wolfgang Pauli, whose exclusion principle was fundamental to the entire theory of degenerate matter, likewise confirmed that the mathematics was sound and the conclusions valid. Paul Dirac, under whose intellectual influence Chandrasekhar had deepened his understanding of quantum mechanics, also recognized the correctness of the work. Leon Rosenfeld, a Belgian physicist who had collaborated with Bohr, was similarly supportive. These men understood the physics in a way that Eddington, for all his brilliance in other areas, perhaps did not, and they recognized that Chandrasekhar had discovered something important and true about the universe, even if the implications were troubling and the ultimate fate of massive stars remained mysterious. But these expressions of support were private, offered in letters and conversations rather than in public forums where they might have countered Eddington's influence, and Chandrasekhar was left largely alone to defend his work against the weight of established authority. He did so with remarkable grace and restraint, never descending to personal attacks or emotional appeals, always maintaining his focus on the scientific substance of the disagreement. He continued to publish his work, to refine his calculations, and to engage with the astronomical community on the merits of the arguments. But the damage had been done, and the field of stellar structure would not fully accept the implications of the Chandrasekhar limit for many years to come. During this difficult period, a source of personal happiness entered Chandrasekhar's life. In 1934, he made a visit to India, and there he met Lalitha Doraiswamy, a young woman who had been a student of physics at Presidency College in Madras. They had known of each other before, but this visit allowed their acquaintance to deepen into something more, and a connection formed between them that would prove lasting and sustaining through all the years to come. Lalitha understood the world of physics and could appreciate the significance of Chandrasekhar's work, and she would become his partner in every sense, supporting him through the disappointments and triumphs of his long career. As the 1930s progressed, Chandrasekhar began to consider his future with increasing seriousness. The Eddington controversy had left its mark, and he could not help but notice that the prospects for an Indian scientist in British academia, even one with a Trinity Fellowship and publications in the leading journals, were limited in ways that had nothing to do with scientific merit. The casual racism of the era, the assumptions about colonial peoples that pervaded British society, the glass ceiling that prevented advancement to the highest positions, all of these factors weighed on his mind as he considered where his career might best flourish. England had given him much: the opportunity to work with great minds, access to the finest libraries and the latest scientific literature, the prestige of Cambridge and the Royal Astronomical Society, but it had also shown him its limitations, its unwillingness to accept the implications of his work when those implications came from an unexpected source, its deference to authority over evidence. By the end of this period, Chandrasekhar had begun to look elsewhere, to consider opportunities in other countries where his talents might be more fully appreciated and where the shadow of the Eddington controversy might be less oppressive. The decision to leave England, when it came, would be shaped by many factors, but among them was surely the memory of that January afternoon in 1935, when his careful work had been dismissed as buffoonery by a man who could not accept where the mathematics led, and when the astronomical community had chosen to follow prestige rather than proof. It was a lesson in the sociology of science, in the way that human factors can delay the acceptance of truth, and it would inform Chandrasekhar's approach to his work for the rest of his life, as he continued to follow the equations wherever they led, trusting in the eventual vindication that comes when nature confirms what mathematics has revealed. In January of 1937, Subrahmanyan Chandrasekhar arrived at the University of Chicago to take up a position on the faculty, and he was assigned to work at the Yerkes Observatory, which was situated not in the city itself but rather in the small town of Williams Bay, in the state of Wisconsin, some 90 miles to the north. The observatory had been established in the 1890s and housed what was then the largest refracting telescope in the world, a great instrument with a lens 40 inches across, and the buildings themselves were set among gentle hills and farmland, beside a lake called Geneva, in a landscape that was quiet and rather removed from the bustle of urban academic life. Chandrasekhar was 26 years old when he arrived, and he would remain affiliated with the University of Chicago for the rest of his career, a span of more than 50 years, though the nature of his work and his physical location within the university's various facilities would change considerably over the decades that followed. The person most responsible for bringing Chandrasekhar to Chicago was Otto Struve, who served as the director of the Yerkes Observatory during this period. Struve was himself a distinguished astronomer, born into a family with a remarkable tradition in the field, as both his grandfather and his great-grandfather had been prominent astronomers in Russia and Germany. Struve had emigrated to the United States following the Russian Revolution and had built the Yerkes Observatory into a center of serious astrophysical research, and he possessed a keen eye for identifying talented young scientists who might contribute to this work. He had followed Chandrasekhar's career with interest, had read the papers on white dwarf stars and stellar masses, and had recognized that here was a theorist of exceptional mathematical ability whose presence would strengthen the observatory's research program. The invitation to join the Chicago faculty represented a significant opportunity, and Chandrasekhar accepted it, though it meant leaving behind Cambridge and England, where he had spent 4 productive years and where he had established himself within the scientific community. Before departing for the United States, Chandrasekhar had returned to India to be married, and the wedding took place on the 11th of September, 1936, in a ceremony that joined him to Lalitha Durayaswamy, whom he had known for some years. They had first met at Presidency College in Madras, where both had been students, she studying physics and he pursuing the mathematical and scientific interests that would eventually lead him to astrophysics. Lalitha was self-trained in the physical sciences, and this shared background meant that she understood the nature of his work and the demands it placed upon his time and concentration. And throughout their long marriage she would provide a quiet and steady companionship that sustained him through the various challenges of academic life. They did not have children, and their household remained a partnership of 2, which perhaps allowed Chandrasekhar to devote himself to his research with a single-mindedness that might otherwise have been difficult to maintain. The marriage endured for more than half a century, until Chandrasekhar's death, and those who knew them remarked upon the evident affection and mutual respect that characterized their relationship, a bond that was undemonstrative but deep. The setting at Williams Bay was quite different from anything Chandrasekhar had experienced before, whether in the busy cities of India or in the ancient university town of Cambridge. Here was rural America, a landscape of farms and small communities, where the winters were long and cold and the nearest large city was a considerable distance away. The observatory itself formed a kind of small academic outpost, with a modest number of astronomers and support staff, and the social world available to its residents was correspondingly limited. For a young couple from India, adjusting to this environment required patience and a certain self-sufficiency, and the isolation could at times feel pronounced, particularly during the winter months when snow covered the fields and travel became difficult. Yet there were compensations as well, for the quiet surroundings allowed for concentrated work without the distractions that a larger institution might have presented, and Chandrasekhar found that he could devote long uninterrupted hours to his calculations and his writing, building up the systematic investigations that would define this period of his career. During these years at Yerkes, Chandrasekhar turned his attention to a comprehensive study of stellar structure, seeking to understand the physical processes that govern how stars are built and how they maintain themselves against the inward pull of gravity. This was in some ways a continuation of his earlier work on white dwarfs, but now he approached the subject more broadly, considering stars of various types and examining the equations that describe the balance between pressure and gravity, between energy generation and energy transport, that must hold within a stable star. He worked with great mathematical care, deriving results from first principles and checking each step of his reasoning with meticulous attention to detail, and the papers he produced during this period reflected this thoroughness. The approach was not flashy or dramatic, but rather steady and cumulative, each investigation building upon those that had come before, and the overall effect was to establish a rigorous foundation for the theoretical understanding of stellar interiors. The culmination of this work was a book published in 1939, titled An Introduction to the Study of Stellar Structure, which gathered together his researches on the subject and presented them in a systematic and unified form. The book was dense with mathematics, filled with equations and derivations that demanded close attention from the reader, and it made no concessions to those who might have wished for a more accessible treatment. Yet for those who were prepared to follow the arguments in detail, the book offered a comprehensive guide to the theory of stellar interiors, covering topics such as the equations of state for stellar material, the mechanisms by which energy is transported from the core of a star to its surface, and the conditions under which stars remain in equilibrium. It became a standard reference in the field, consulted by generations of astrophysicists who wished to understand the fundamental principles governing stellar behavior, and its influence persisted for many decades. The writing was clear but demanding, and the overall impression was one of a subject that had been thoroughly mastered and then carefully explained, with every loose end tied up and every assumption made explicit. Chandrasekhar's life in America during these years was not without difficulties that arose from matters quite separate from his scientific work. The United States in the 1930s and 40s was a country where racial prejudice was pervasive and openly expressed, and a man of Indian origin, with dark skin and a foreign accent, encountered attitudes and barriers that his white colleagues did not face. There were hotels that would not accommodate him, restaurants where he was not welcome, and social situations in which the assumptions of racial hierarchy made themselves felt in ways both subtle and overt. Chandrasekhar did not speak of these experiences often or at length, preferring to maintain his dignity and to focus upon his work. But those who knew him understood that such encounters occurred and that they left their mark. The decision to remain in the United States rather than return to India, which he might have done, reflected a complex weighing of opportunities and obstacles, and the scientific resources available at a major American research institution were considerable factors in that calculation. He became a naturalized citizen of the United States in 1953, formally committing himself to the country that had provided him with a platform for his work, even as that country had not always treated him with the respect he deserved. When the Second World War began, the normal patterns of academic life were disrupted, and many scientists found themselves drawn into work related to the war effort. Chandrasekhar was among those who contributed in this way, and from 1943 to 1945 he was engaged in research at the Aberdeen Proving Ground in Maryland, a military facility where weapons and ammunition were tested and where scientific expertise was applied to problems of ballistics and explosives. The specific work he undertook there involved the study of shock waves and the behavior of projectiles, subjects that might seem distant from the stars and their structure, but that in fact drew upon many of the same mathematical techniques. The equations governing the propagation of a shock wave through air, for instance, involve considerations of fluid dynamics and thermodynamics that are not entirely unlike those that arise in the study of stellar atmospheres, and Chandrasekhar brought to these military problems the same rigorous analytical approach that characterized his astrophysical research. The work at Aberdeen was classified and not published in the open scientific literature, but it was regarded as valuable by those who oversaw the research programs there, and Chandrasekhar's contributions were recognized as significant. He applied himself to the task with his customary thoroughness, deriving results and solving equations with the precision that was his hallmark, and the mathematical formalism he developed for treating certain aspects of ballistic problems was noted for its elegance and its utility. It was perhaps an unusual deployment of talents that had been developed for understanding the cosmos, but wartime created its own imperatives, and Chandrasekhar, like many of his scientific contemporaries, set aside his usual investigations to assist in the collective effort. When the war ended, he returned to the Yerkes Observatory and to his astronomical work, and the wartime research became a closed chapter, rarely discussed in later years but forming part of the larger pattern of his contributions to science in its various applications. Throughout this period, from his arrival in 1937 to the end of the war in 1945, Chandrasekhar was building a reputation that rested not upon dramatic announcements or striking personal charisma, but rather upon the steady accumulation of careful, detailed, and exhaustive work. He published paper after paper, each one addressing some specific aspect of stellar theory, each one working through the mathematics with patient thoroughness, and the collective effect was to establish him as a figure of considerable authority in his field. He was not given to self-promotion or to the cultivation of a public persona, preferring instead to let the work speak for itself, and the work did indeed speak, though perhaps more quietly than the productions of some other scientists. Those who read his papers and his books recognized the quality of the thinking behind them, the refusal to cut corners or to gloss over difficulties, and this recognition formed the foundation of a reputation that would continue to grow in the years that followed. The life he and Lalitha established at Williams Bay was a quiet one, centered upon the observatory and the small community that surrounded it, and the rhythms of their days were shaped by the demands of his research and by the cycle of the academic year. They made a home in that remote place, adapting themselves to the climate and the customs of rural Wisconsin, and the distance from Chicago, though sometimes inconvenient, also provided a kind of shelter from the distractions that a larger city might have offered. Chandrasekhar worked long hours, as he always had and always would, and the books and papers that emerged from his study during these years represented the visible fruits of that labor. Behind them lay countless calculations, pages of algebra, careful checking and rechecking of results, and the slow patient effort of understanding that was his characteristic mode of engaging with the physical world. The years at Yerkes formed a foundation upon which much else would later be built, and the work he accomplished there would continue to influence the field of astrophysics long after he had moved on to other problems and other investigations. In the years following the Second World War, Subrahmanyan Chandrasekhar turned his attention to a problem that had quietly frustrated physicists and astronomers for many decades, and this was the problem of understanding how light and heat move through matter, how radiation travels through gases and atmospheres, how energy makes its long and winding journey from the interior of a star to its visible surface and then outward into the cold reaches of space. This field, known as radiative transfer, might sound rather technical at first mention, and indeed it is filled with equations and careful mathematical reasoning. But at its heart it asks a question that is almost poetic in its simplicity, which is to say, how does light find its way through the universe, and what happens to it along the way, as it passes through clouds of gas, through stellar atmospheres, through the thin veils of matter that hang between the stars? Chandrasekhar approached this subject with the same methodical intensity that had characterized all of his previous work, beginning with the fundamental equations that describe how photons of light interact with the atoms and electrons they encounter, how they are absorbed and scattered and re-emitted, how they gradually work their way through what physicists call an optically thick medium, which is simply a region where light cannot pass through freely but must instead undergo many interactions before emerging on the other side. The mathematics of these processes had been studied before, of course, by researchers such as Arthur Schuster and Carl Schwarzschild and Arthur Eddington himself, but the general solutions to the equations of radiative transfer had remained elusive, and many special cases that arose in practical astrophysical situations had never been properly solved. What Chandrasekhar did during these years was to develop entirely new mathematical methods for attacking these problems, methods that were systematic and rigorous and that could be applied not just to one particular situation but to whole classes of related problems. He introduced what became known as the discrete ordinate method, which is a technique for replacing the continuous range of directions in which light can travel with a finite set of representative directions, thereby transforming the intractable integro-differential equations of radiative transfer into systems of ordinary differential equations that could actually be solved. This might sound like a mere computational trick, a simplification for convenience, but it was in fact a profound insight into the mathematical structure of the problem, and the solutions obtained by this method turned out to be remarkably accurate and useful for real astrophysical calculations. He also developed the method of invariant embedding, which approaches radiative transfer problems by considering how the properties of an atmosphere change as one imagines adding thin layers to it, building up the solution incrementally rather than trying to solve everything at once. And he introduced what are now called the h functions and the x and y functions, which are special mathematical functions that arise naturally in the theory of radiative transfer and that encode in elegant form the solutions to many different problems in the field. These functions have a kind of mathematical beauty to them, a self-consistency and symmetry that Chandrasekhar found deeply satisfying, and they have become standard tools in the field, appearing in textbooks and research papers to this day. All of this work culminated in the publication, in 1950, of a book simply titled Radiative Transfer, which immediately became and has remained the definitive treatise on the subject. The book is not light reading, as one might imagine, being filled with equations and derivations and careful mathematical arguments, but it has a certain clarity and completeness to it that makes it invaluable to anyone who needs to understand how radiation moves through matter. Chandrasekhar solved in this book problems that had frustrated physicists for decades, and he did so with a thoroughness that left little room for others to improve upon his work. The book became a classic not just in astrophysics but in related fields such as atmospheric science and nuclear reactor theory, wherever the transport of radiation or particles through matter needs to be understood. This pattern of choosing a field, working on it exhaustively for approximately a decade, writing a definitive monograph that summarized everything he had learned, and then moving on to an entirely new subject, was by now clearly established as Chandrasekhar's characteristic mode of working. He had done it with stellar structure in the 1930s, and he had done it with stellar dynamics in the early 1940s, publishing in 1942 a book called Principles of Stellar Dynamics, which dealt with the gravitational interactions of stars in clusters and galaxies, how stars move under one another's gravitational influence, how stellar systems evolve over time. And now he had done it again with radiative transfer, producing another monumental work that would stand as the authoritative reference for generations. This method of working was quite unusual among scientists, most of whom tend to find a field they enjoy and remain in it for their entire careers, building up expertise and reputation in one area. Chandrasekhar deliberately chose to abandon each field once he felt he had mastered it, to leave behind his contributions and start fresh in some new area where he would once again be a beginner. He spoke about this approach in later years, explaining that he did not wish to become stale, to keep going over the same ground, to become merely a guardian of his past achievements rather than a seeker of new understanding. There is something both admirable and slightly melancholic about this discipline, this willingness to walk away from years of accumulated knowledge and start again from the beginning. During this period, Chandrasekhar also made important contributions to our understanding of a particular atomic species that turned out to be crucial for the theory of stellar atmospheres, and this was the negative hydrogen ion. Now a hydrogen atom, as you may recall from basic chemistry, consists of a single proton with a single electron orbiting around it, and it is electrically neutral because the positive charge of the proton exactly balances the negative charge of the electron. But it turns out that under certain conditions, a hydrogen atom can capture a second electron, becoming what is called a negative hydrogen ion, with a net negative charge. This might seem like a minor curiosity, but Chandrasekhar showed that the negative hydrogen ion is actually extremely important for understanding the opacity of stellar atmospheres, which is to say, for understanding how easily light can pass through the outer layers of stars like our own Sun. The opacity of a gas determines how far light can travel through it before being absorbed or scattered, and this in turn determines how energy flows through stellar atmospheres and how the temperature varies with depth. If you get the opacity wrong, your whole model of the star will be wrong. So understanding the sources of opacity is crucial for stellar astrophysics. Chandrasekhar's careful calculations of the properties of the negative hydrogen ion, including how easily it absorbs light of different wavelengths, proved essential for building accurate models of the Sun and similar stars, and his work on this problem is still cited and used today. In 1952, Chandrasekhar made a physical move that reflected a transition in his career, leaving the Yerkes Observatory in Williams Bay, Wisconsin, where he had worked since 1937, and relocating to the main campus of the University of Chicago in the city itself. Yerkes had been a productive and relatively peaceful place to work, with its large refracting telescope and its small community of astronomers, but the isolation of Williams Bay, pleasant as it might have been for concentrated research, was perhaps becoming less suitable for someone who was now one of the leading figures in theoretical astrophysics. The move to Chicago brought him closer to colleagues in physics and mathematics, and to the wider intellectual life of a great university. That same year, 1952, Chandrasekhar took on a responsibility that would occupy a significant portion of his time and energy for nearly 2 decades, and this was the position of managing editor of the Astrophysical Journal, which was then and remains today one of the most important scientific journals in astronomy and astrophysics. Under his editorship, which lasted until 1971, the journal was transformed from a respectable but somewhat provincial American publication into the leading international journal in the field, the place where the most important results were published, the standard against which other journals were measured. Chandrasekhar brought to this editorial role the same exacting standards and legendary attention to detail that characterized his own scientific work. He read every paper submitted to the journal, not superficially but carefully, checking the mathematics, questioning the assumptions, demanding clarity and rigor from the authors. His letters to authors were famous, or perhaps infamous, for their length and thoroughness, pointing out errors and inconsistencies, suggesting improvements, sometimes requiring extensive revisions before a paper could be accepted. Many astronomers have stories of receiving thick envelopes from the Astrophysical Journal, filled with page after page of closely written comments in Chandrasekhar's distinctive hand. This might sound rather intimidating, and no doubt it was for many authors, but the effect on the quality of the journal was unmistakable. Papers published in the Astrophysical Journal during Chandrasekhar's editorship could be trusted to have been carefully vetted, to have been checked for errors, to meet a high standard of scientific quality. The journal's reputation soared, and it attracted the best work from astronomers around the world. This was in many ways a selfless contribution to the field, since the countless hours Chandrasekhar spent reading and commenting on other people's papers were hours he could not spend on his own research. But he seems to have viewed it as a duty, as something that needed to be done properly if the field was to advance. Among the students who worked with Chandrasekhar during this period was Donald Osterbrock, who went on to become a distinguished astronomer himself, known for his work on gaseous nebulae and the history of American astronomy. Osterbrock later wrote about what it was like to be a student of Chandrasekhar, describing the rigor and intensity of the experience, the high expectations, the sense that one was being trained not just to solve problems but to think deeply and systematically about the natural world. Chandrasekhar was not an easy teacher, by all accounts, but he was a thorough one, and the students who survived his demanding approach came away well prepared for their own careers in research. The discipline of completely abandoning each field after mastering it continued to shape Chandrasekhar's career during these years. Having finished with radiative transfer, having written the book that would define the field for decades, he was already looking ahead to new problems, new areas where his mathematical skills could be brought to bear. He did not rest on his laurels, did not spend his time defending or extending his past work, but instead looked for fresh challenges, for problems that would require him to learn new things and develop new techniques. There is a famous statement attributed to Chandrasekhar about this habit of leaving behind his contributions, about the strange discipline of walking away from fields he had spent years mastering. He spoke of how each area of work was like a garden that he had tended and cultivated, bringing it to fruition, and then had to leave for others to enjoy while he went off to break new ground elsewhere. Whether this was entirely by choice or partly by temperament, whether it reflected confidence or restlessness or some combination of the two, it certainly gave his career a distinctive shape, a series of peaks rather than a single long ridge, each peak representing a different field that he had climbed and then descended. As the 1950s drew toward their close, Chandrasekhar was already deep into his next great project, which would take him into the mathematical theory of hydrodynamic and hydromagnetic stability, the study of when and how flowing fluids become unstable, when smooth flows break down into turbulence, when the delicate balance of forces in a star or a planet is disrupted. But that is a story for another time, another chapter in this long and productive life. For now, it is enough to note that the pattern was set, the method was established, and Chandrasekhar continued to follow it with remarkable discipline and consistency, moving from field to field, leaving behind definitive works, and always seeking new problems worthy of his formidable intellect. In the early 1960s, Subrahmanyan Chandrasekhar turned his attention to a field that might seem, at first consideration, rather distant from the stellar interiors and white dwarfs that had occupied his younger years, and yet this new direction was connected to everything he had studied before, in the way that water is connected to rivers and rivers to the sea. The field was hydrodynamic stability, which is the study of when and how fluids remain in steady, predictable states, and when and how they depart from such states into turbulence and complexity. It is a subject as old as the observation of smoke rising from a candle, which rises smoothly for a time and then, at some height, begins to curl and twist and break apart into eddies and whirls that seem to follow no simple pattern at all. Chandrasekhar approached this ancient puzzle with the same methodical thoroughness he had brought to everything else, and by 1961 he had produced another of his comprehensive treatises, a volume titled Hydrodynamic and Hydromagnetic Stability, which gathered together the scattered knowledge of the field and organized it into a coherent and mathematically rigorous whole. This book, like his earlier works on stellar structure and radiative transfer, became a standard reference for generations of researchers who came after him. It is a dense and careful volume, not written for casual reading but for serious study, and it treats its subjects with the kind of exhaustive attention that leaves no loose threads hanging. The The stability of fluids is a matter of considerable importance in many areas of science and engineering, from the design of aircraft wings to the behavior of the atmosphere to the dynamics of stars and galaxies. And Chandrasekhar's treatise provided a unified framework for understanding the underlying mathematics. He examined the conditions under which a fluid at rest will remain at rest when slightly disturbed, and the conditions under which such a disturbance will grow and amplify until the original state is entirely destroyed and replaced by something more complicated. These questions had been studied piecemeal by many investigators over many decades, but Chandrasekhar brought to them his characteristic desire for completeness and logical order, and the result was a book that one could begin at the beginning and read through to the end with the sense that nothing essential had been omitted. The study of hydrodynamic stability naturally extends into hydromagnetic stability, which is the stability of electrically conducting fluids in the presence of magnetic fields. When a fluid can carry electrical currents, as plasmas and liquid metals can, then the magnetic fields threading through that fluid become part of the dynamical system, influencing the motion of the fluid and being influenced by it in turn. This coupling of fluid motion and magnetic field is described by the equations of magnetohydrodynamics, a set of mathematical relationships that Chandrasekhar found particularly appealing for their elegance and their difficulty. The stability problems in magnetohydrodynamics are considerably more intricate than those in ordinary hydrodynamics, because one must account not only for the usual forces of pressure and viscosity and gravity, but also for the electromagnetic forces that arise whenever currents flow through magnetic fields. Chandrasekhar devoted substantial effort to understanding how magnetic fields can stabilize or destabilize fluid configurations, and his treatise includes extensive discussions of such problems. Among the topics he treated with particular care was the stability of rotating fluid masses, a subject of direct relevance to the shapes and behaviors of stars and planets. A rotating body of fluid tends to flatten at the poles and bulge at the equator, and if it rotates rapidly enough, it may become unstable and break apart or distort into non-axisymmetric shapes. These questions had fascinated mathematicians since the time of Newton and had been studied by many of the great figures of classical mechanics, including Jacobi and Riemann and Poincare. Chandrasekhar returned to these classical problems with modern methods and extended them into the realm of magnetohydrodynamics, where the presence of magnetic fields introduces new possibilities and new complications. He asked what happens when a rotating fluid mass is also threaded by magnetic field lines, and how the interplay of rotation and magnetism affects the stability of the configuration. These are not merely academic exercises. 4 rotating magnetized fluids are found throughout the universe, in the cores of stars and in accretion disks around compact objects and in the vast tenuous plasmas that fill interstellar space. It is worth pausing here to mention a collaboration that had taken place some years earlier, before this period of concentrated work on stability theory, a collaboration that illustrates both Chandrasekhar's breadth of interests and his ability to work productively with scientists of very different temperaments and styles. In the early 1950s, Chandrasekhar worked together with Enrico Fermi on problems related to magnetic fields in the spiral arms of galaxies. Fermi was one of the most celebrated physicists of the 20th century, known for his contributions to nuclear physics and particle physics, and for his leadership of the project that produced the first controlled nuclear chain reaction. He was a very different kind of scientist from Chandrasekhar, more intuitive and less formal, more inclined to quick estimates and physical reasoning than to exhaustive mathematical analysis. And yet the two men found common ground in their interest in astrophysical problems, and together they developed what became known as the Chandra-Fermi mechanism for the acceleration of cosmic rays. Cosmic rays are particles, mostly protons, that travel through space at extremely high energies, some of them far exceeding the energies achievable in any particle accelerator built by human hands. The origin of these energetic particles was a puzzle, and Fermi had proposed a mechanism by which particles could be accelerated to high energies through repeated interactions with moving magnetic fields in interstellar space. Chandrasekhar and Fermi worked together to develop and refine this idea, examining how particles might gain energy by bouncing off magnetic irregularities embedded in the interstellar medium. Their collaboration was fruitful but brief, for Fermi died in 1954 at the age of 53, of stomach cancer, and Chandrasekhar was deprived of a colleague whose physical intuition complemented his own mathematical rigor. The Chandra-Fermi mechanism remains an important concept in high-energy astrophysics, and it stands as a testament to what can be achieved when scientists of different styles bring their complementary strengths to bear on a common problem. Throughout these years, and indeed throughout his entire career, Chandrasekhar was known for his extraordinary dedication to teaching. His lectures were not casual or improvised affairs but carefully prepared performances, in the sense that a symphony performance is carefully prepared, with every note considered and every transition planned. He would derive every equation in full, step by step, never skipping over the difficult parts or leaving the derivation as an exercise for the reader. His blackboard work was meticulous, and students who attended his courses often felt that they were witnessing something approaching perfection in pedagogical craft. He did not simply explain the results of physics but showed how those results were obtained, leading his students through the mathematical reasoning with patience and clarity. This approach required enormous preparation, and Chandrasekhar was known to spend many hours preparing for each lecture, working through the derivations himself until he could present them smoothly and without hesitation. His students benefited immensely from this approach, and many of them went on to distinguished careers of their own. Among those who studied with him during this period were Norman Leibovitz, who became a noted applied mathematician and worked on problems of rotating fluid masses and their stability, and Roger Blandford, who would become one of the leading astrophysicists of the late 20th and early 21st centuries, known for his work on active galactic nuclei and relativistic jets. These students and others absorbed not only the technical content of Chandrasekhar's courses, but also something of his attitude towards scientific work, his insistence on thoroughness and rigor, and his belief that understanding comes through careful and patient effort, rather than through shortcuts and approximations. There is a story, often told, about Chandrasekhar's dedication to his students that deserves mention here, even though it refers to events somewhat earlier than the period we are now considering. In the late 1940s, Chandrasekhar was based at the Yerkes Observatory in Williams Bay, Wisconsin, a small town about 80 miles north of Chicago. The university also maintained its main campus in Chicago, and Chandrasekhar agreed to teach a course on astrophysics for graduate students there. Only 2 students registered for the course, but Chandrasekhar did not cancel it or ask the students to come to him. Instead, he drove the 100-mile round trip from Williams Bay to Chicago and back, through the winter snows of the upper Midwest, to teach his class of 2. Those 2 students were Chen-Ning Yang and Tsung-Dao Lee, and in 1957 they would share the Nobel Prize in Physics for their work on the violation of parity conservation in weak interactions. Chandrasekhar never made much of this story himself, regarding the teaching of students, however few, as simply part of his duty as a professor, but it has become one of the legendary anecdotes of 20th century physics, a small illustration of the seriousness with which he approached every aspect of his work. During this period, Chandrasekhar received recognition from many quarters for his contributions to science. In 1944, he had been elected a Fellow of the Royal Society of London, one of the oldest and most prestigious scientific societies in the world, a recognition of the fundamental importance of his work on white dwarfs and stellar structure. In 1966, he received the National Medal of Science from the President of the United States, the highest honor bestowed by the American government for achievement in science. These awards and honors accumulated over the years, and Chandrasekhar accepted them with characteristic modesty, always returning to his work and to his students rather than dwelling on accolades. And yet, even as he worked on hydrodynamic stability and plasma physics and the many other subjects that drew his attention during these years, there was a thread of thought that he had never entirely abandoned, a problem that lay in the background of his mind, waiting. It was the problem of gravitational collapse, the fate of stars too massive to become white dwarfs, the question that Arthur Eddington had dismissed so contemptuously in 1935. Chandrasekhar had shown, as a young man, that there was an upper limit to the mass of a white dwarf, beyond which the electron degeneracy pressure could not support the star against its own gravity. Eddington had rejected this conclusion, not because of any mathematical error, but because he found the physical implications unacceptable. He could not believe that a star would simply continue collapsing without limit, shrinking down to a point of infinite density, and he insisted that some new physics must intervene to prevent such an outcome. Chandrasekhar had not argued publicly with Eddington, and after the controversy he had moved on to other subjects, applying his mathematical gifts to radiative transfer and stellar dynamics and hydrodynamic stability. But the question had not disappeared from physics. Other researchers had taken up the problem, and by the 1960s it was becoming clear that gravitational collapse was not merely a theoretical curiosity but a real phenomenon with observable consequences. The objects that would come to be called neutron stars and black holes were gradually emerging from the realm of speculation into the realm of serious astrophysical investigation. Chandrasekhar began to turn his attention back to these questions, to the relativistic theory of gravitation and its implications for the final states of massive stars. It was a gradual return, a slow circling back to the problems of his youth, approached now with the accumulated experience and mathematical sophistication of a lifetime. This return to gravitational physics would occupy much of his later career and would eventually produce another of his great treatises, but that work lay still in the future. For now, in the 1960s and early 70s, he was completing his systematic study of stability and laying the foundations for what was to come. The work was patient and unhurried, as all his work was, and it proceeded with the same careful attention to completeness and rigor that had characterized everything he had done before. The universe is full of fluids and plasmas and magnetic fields, and understanding their behavior requires precisely the kind of thorough mathematical analysis that Chandrasekhar was so well suited to provide. In the early 1970s, when Subrahmanyan Chandrasekhar had already completed several distinct careers within the single span of his scientific life, he found himself drawn back toward a subject he had not studied in depth for nearly 4 decades: the theory of collapsed stellar objects, which he had first explored as a young man aboard a ship crossing the Arabian Sea, had transformed utterly in the intervening years, and the field of relativistic astrophysics now occupied a central place in modern physics that would have seemed scarcely imaginable when Arthur Eddington had dismissed the limiting mass with such theatrical certainty. Chandrasekhar was in his early 60s when he began this return to the territory of his youth, and he approached the mathematical theory of black holes with the same methodical thoroughness that had characterized all his previous investigations into stellar structure, radiative transfer, hydrodynamic stability, and the equilibrium figures of rotating fluid masses. The transformation of the field since 1935 had been remarkable in ways both scientific and cultural. Theoretical developments by Carl Schwarzschild, Roy Kerr, Roger Penrose, Stephen Hawking, and many others had established a rigorous mathematical framework for understanding the geometry of spacetime around collapsed objects, while observational advances had revealed phenomena in the distant universe that seemed to require the existence of extraordinarily compact concentrations of matter and energy. The term black hole itself had been coined only in 1967 by John Archibald Wheeler, and this memorable phrase had helped to bring these strange objects into the awareness of the general public in ways that earlier, more technical terminology had never achieved. Quasars, pulsars, X-ray binaries, and other newly discovered astronomical systems all pointed toward the reality of gravitational collapse on scales ranging from individual stellar remnants to the centers of entire galaxies, and the collapsed configurations that had once seemed to Eddington an absurd mathematical fiction were now understood to be not merely possible but apparently inevitable outcomes of stellar evolution for stars of sufficient mass. Chandrasekhar undertook to master the subject of general relativity with the systematic approach that had served him so well throughout his career, working through the mathematical foundations with care and patience rather than relying on the more informal methods that sometimes characterized research in the rapidly developing field. He immersed himself in the geometry of curved spacetime, in the tensor calculus that provided the natural language for describing gravitational phenomena, and in the specific solutions to Einstein's field equations that described the spacetime around non-rotating and rotating black holes. The Schwarzschild solution, which describes the geometry outside a spherically symmetric, non-rotating mass, had been known since 1916, but the more general Kerr solution, which describes the spacetime around a rotating black hole, had been discovered only in 1963, and this solution presented mathematical complexities that invited the kind of thorough, methodical analysis at which Chandrasekhar excelled. The Kerr black hole, named for the New Zealand mathematician Roy Kerr who first derived its geometry, possesses features that distinguish it fundamentally from its non-rotating counterpart. A rotating black hole drags spacetime itself around with it, creating a region called the ergosphere where nothing can remain stationary relative to distant observers, and the mathematical description of this dragging effect and its consequences required sophisticated techniques that Chandrasekhar set about developing and extending. The perturbation theory of black holes, which describes how these objects respond to small disturbances and how waves propagate in their vicinity, became a particular focus of his attention, and he developed new mathematical approaches that brought greater clarity and rigor to calculations that had previously been carried out by more approximate methods. For approximately 8 years, Chandrasekhar devoted himself to this intensive study, working with characteristic concentration and discipline to produce a comprehensive treatment of black hole physics that would present the subject in a form both mathematically complete and logically coherent. He was not content merely to summarize the existing literature or to collect the scattered results of other researchers, but sought instead to rederive everything from first principles, to verify each calculation independently, and to present the material in a unified framework that revealed the underlying mathematical structure of the theory. This approach required extraordinary patience and persistence, and the years of concentrated effort produced a work of scholarship that reflected both the depth of Chandrasekhar's mathematical ability and the breadth of his determination to understand the subject completely. The mathematical theory of black holes was published in 1983. Appearing as a substantial volume that immediately became the standard reference for researchers working in relativistic astrophysics and gravitational physics. The book presented a comprehensive treatment of the Schwarzschild and Kerr solutions, of the perturbation theory describing how these spacetimes respond to disturbances, and of the mathematical techniques necessary for analyzing the propagation of gravitational, electromagnetic, and other waves in the vicinity of black holes. Chandrasekhar's characteristic style was evident throughout, with the systematic development from fundamental principles, the careful attention to mathematical detail, and the insistence on treating each problem completely rather than leaving loose ends for others to tie up. The work was demanding, requiring considerable mathematical sophistication from its readers, but it provided a foundation on which subsequent research could be built with confidence in the solidity of the underlying structure. The sense of vindication that Chandrasekhar must have felt, though he rarely spoke of it directly, can perhaps be glimpsed in the dedication with which he pursued this return to the subject of collapsed stellar objects. The white dwarf stars whose internal constitution he had analyzed as a young man, and whose limiting mass he had calculated with such care during that sea voyage from India to England, were now understood to be merely one possible endpoint of stellar evolution, with neutron stars and black holes representing the fates of more massive stellar cores. The objects that Eddington had dismissed as absurdities, claiming that nature would find some way to prevent such gravitational collapse, were now observed throughout the universe, and the mathematical theory describing their properties had become a major branch of theoretical physics. Chandrasekhar had lived to see the complete rehabilitation of the ideas that had been so publicly and so dismissively rejected at that meeting in Burlington House nearly half a century earlier, and his return to the subject in his 60s and 70s represented a kind of completion, a closing of a circle that had been opened in his youth. In October of 1983, during the same year that saw the publication of the mathematical theory of black holes, the Royal Swedish Academy of Sciences announced that Subrahmanyan Chandrasekhar would share the Nobel Prize in Physics with William Alfred Fowler. The announcement came on the 19th of October, which happened to be Chandrasekhar's 73rd birthday, a coincidence that added a personal note to the recognition of his scientific achievements. The prize citation honored him for his theoretical studies of physical processes important to the structure and evolution of stars, a formulation that encompassed the work on white dwarfs and stellar structure that had occupied his early career, and that implicitly acknowledged the correctness of the conclusions that had been so controversially received in 1935. William Fowler, with whom Chandrasekhar shared the prize, had made fundamental contributions to understanding the nuclear reactions that power stars and that synthesize the heavy elements found throughout the universe, work that complemented in important ways the investigations of stellar structure to which Chandrasekhar had devoted his early decades. The two lines of research, one concerning the internal constitution and stability of stars, and the other concerning the nuclear processes that provide stellar energy and create new atomic nuclei, together formed a comprehensive picture of how stars live and die, and the joint award recognized both aspects of this understanding. The citation did not specifically mention black holes or the limiting mass, but the recognition of Chandrasekhar's work on stellar evolution necessarily implied acknowledgement of the conclusions about gravitational collapse that had proved so controversial so many years before. Chandrasekhar's response to the Nobel Prize was characteristically measured and restrained. He did not use the occasion to express triumph over those who had opposed his early work, nor did he dwell publicly on the bitterness that the Eddington episode must have caused him. In interviews and in his Nobel lecture, he maintained the dignified reserve that had characterized his public demeanor throughout his career, focusing on the scientific content of his work rather than on the personal history of controversy and vindication. This restraint was consistent with the approach he had taken for nearly 50 years, never publicly attacking Eddington even when opportunities presented themselves, and never allowing personal grievance to color his scientific presentations. Whether this measured response reflected genuine equanimity, deliberate self-discipline, or simply an unwillingness to revisit painful memories in public, the effect was to maintain a focus on the science itself rather than on the human drama surrounding it. His Nobel lecture, titled On Stars, Their Evolution and Their Stability, presented a survey of the developments in stellar astrophysics to which he had contributed, tracing the progress of understanding from the early work on white dwarfs through the later investigations of stellar stability and evolution. The lecture was delivered in Stockholm in December of 1983, in the formal setting of the Nobel ceremonies, and it reflected both the depth of Chandrasekhar's knowledge and his characteristic concern for clarity and logical development. Lalitha accompanied him to Stockholm for the ceremonies, sharing in the recognition of a lifetime of scientific achievement that had begun when they were both young in Madras and that had continued through more than 4 decades of partnership in Chicago. The Nobel Prize, significant as it was, did not mark the end of Chandrasekhar's active scientific work. He continued his research in the years following the award, maintaining the pattern of sustained intellectual effort that had characterized his entire career. The honor brought increased public recognition and numerous invitations for lectures and interviews, but Chandrasekhar remained committed to the actual practice of science rather than to the ceremonial role of scientific elder statesman. He understood, perhaps better than most, that prizes and honors were acknowledgments of past achievements rather than contributions to future progress, and he continued to approach his work with the same discipline and concentration that he had brought to it throughout his life. The decade of work on black holes that culminated in the 1983 book and the Nobel Prize represented one of the most remarkable episodes in a career filled with remarkable episodes. That a scientist in his 60s could master a complex new field, make original contributions to its mathematical foundations, and produce a definitive reference work was unusual by any standard, and it demonstrated the extraordinary intellectual capacity that Chandrasekhar had maintained throughout his long life. The return to relativistic astrophysics after so many years away from the subject also carried emotional significance that went beyond the purely scientific, allowing him to engage once more with the phenomena that had first captured his imagination as a young man and to contribute to the understanding of objects whose very existence had been denied by those who should have recognized the validity of his early work. In the quiet of his study at the University of Chicago, where he continued to work through the 1980s, Chandrasekhar could reflect on a scientific journey that had begun more than half a century earlier on a ship steaming westward from India. The young man who had calculated the limiting mass during that voyage had become one of the most honored scientists of his generation, and the ideas that had been dismissed with such confidence by the greatest astrophysicist of the age had proved to be not merely correct but fundamental to the modern understanding of the universe. The black holes that now seem to lurk at the centers of galaxies and to punctuate the stellar populations of the Milky Way were the descendants, in a sense, of those calculations performed by a 19-year-old on his way to Cambridge, and their mathematical theory had now received its most complete and rigorous treatment in the book that bore Chandrasekhar's name. The circle had indeed closed, though the work itself, as always, continued. In the final decade of his life, Subrahmanyan Chandrasekhar turned his attention to what might seem, at first glance, an unusual project for a theoretical astrophysicist approaching his 80th year. He decided that he wanted to understand, truly and completely, the geometric methods that Isaac Newton had employed in the Principia Mathematica, that foundational text of modern physics published in 1687. This was not a casual interest or a light retirement hobby. but rather a serious scholarly undertaking that would occupy him for nearly 10 years and result in a substantial book of his own. Chandrasekhar had always possessed a deep reverence for the history of his discipline, and he believed that returning to the original sources, to the very wellsprings of physical understanding, was essential for any scientist who wished to comprehend the true nature of their work. The Principia had long been considered one of the most difficult scientific texts ever written, not because its conclusions were obscure, but because Newton had chosen to present his arguments using the geometric methods of the ancient Greeks rather than the calculus he himself had invented. This choice, whether made from preference or from a desire to ground his work in established mathematical traditions, meant that generations of physicists had learned Newtonian mechanics through later reformulations, while the original text remained largely unread, a monument more often admired from a distance than actually visited. Chandrasekhar found this state of affairs somewhat troubling, and he set himself the task of working through every proposition, every lemma, every corollary in the Principia, translating Newton's geometric arguments into the modern mathematical language that contemporary physicists could readily follow. This undertaking required him to teach himself the geometric methods that Newton had used, a style of reasoning that had fallen out of fashion in physics education centuries earlier. Chandrasekhar approached this self-education with the same methodical patience he had brought to every previous subject, working through the propositions one by one, often spending weeks on a single proof until he felt he understood not merely what Newton had demonstrated but why Newton had chosen that particular path of reasoning. He found the experience deeply rewarding in ways that surprised even himself, discovering in Newton's geometric arguments an elegance and directness that the later algebraic treatments had sometimes obscured. There was something satisfying, he felt, about following the same logical steps that Newton's own mind had traced 3 centuries earlier. The result of this decade of study was a book titled Newton's Principia for the common reader, published in 1995, the final year of Chandrasekhar's life. The title was perhaps slightly misleading, for this was not a popular account aimed at general audiences, but rather a detailed scholarly work that rendered Newton's proofs accessible to physicists and mathematicians who lacked training in classical geometry. Each of Newton's propositions was presented first in its original form, then translated into modern notation, with Chandrasekhar's commentary illuminating the logical structure and physical significance of the arguments. The book represented an extraordinary labor of love, a gift from one great physicist to the memory of another across a span of 300 years. Throughout these final years, Chandrasekhar also continued to reflect on questions that had occupied him intermittently throughout his career, questions concerning the nature of scientific creativity and its relationship to aesthetic experience. These reflections found expression in several essay collections, most notably Truth and Beauty, Aesthetics and Motivations in Science, published in 1987. In these essays, Chandrasekhar explored a theme that had fascinated him since his youth, the curious and persistent role that considerations of beauty and elegance play in the development of physical theories. He observed that the great physicists and mathematicians, when describing their most significant discoveries, often spoke in terms that would be more familiar in discussions of art or music, invoking concepts like harmony, simplicity, and inevitability. Chandrasekhar did not claim that beauty was a reliable guide to truth, for he was well aware that nature might be under no obligation to arrange itself according to human aesthetic preferences. But he noted that, historically, the theories that had proved most durable and most fruitful were often those that possessed a certain mathematical elegance, a quality that was difficult to define precisely but that working scientists seemed to recognize intuitively. He quoted the physicist Paul Dirac, who had once remarked that it was more important to have beauty in one's equations than to have them fit experiment, a statement that Chandrasekhar found provocative, even if he might not have endorsed it quite so boldly. The relationship between aesthetic appeal and physical truth remained, for Chandrasekhar, a genuine mystery, one that seemed to hint at some deep connection between the structure of human cognition and the structure of the physical world. His interest in aesthetics extended well beyond the boundaries of science. Throughout his life, Chandrasekhar had cultivated a deep appreciation for literature and music, finding in these arts a nourishment that complemented his scientific work. He was particularly devoted to the plays of William Shakespeare, which he read and reread throughout his life, finding in them an inexhaustible richness of language and insight into human nature. He admired the way Shakespeare could compress profound observations about the human condition into a few lines of verse, achieving a kind of economy that Chandrasekhar associated with the best scientific theories. There was, he felt, a kinship between the poet's search for the exactly right word and the physicist's search for the exactly right equation. He was equally devoted to Western classical music, and among composers, he felt a particular affinity for Ludwig van Beethoven. The late string quartets especially move him, those difficult and transcendent works that Beethoven composed in his final years while completely deaf, communicating with a world he could no longer hear. Chandrasekhar found in these quartets a quality he could only call sublime, a reaching towards something beyond ordinary human experience that resonated with his own sense of what the greatest scientific achievements might touch upon. He would listen to recordings of these works in his study, finding in them a kind of spiritual sustenance that he could not easily put into words. Even as he pursued these humanistic interests, Chandrasekhar maintained a work schedule that would have exhausted a much younger man. He continued to rise early, to spend long hours at his desk, to hold himself to standards of productivity that his colleagues found remarkable and perhaps slightly alarming. His office at the University of Chicago remained the center of his professional life, a quiet space filled with books and papers where he could think without interruption. He had occupied this office for decades, and it had become as familiar to him as his own home, a place where the rhythms of intellectual work had worn comfortable grooves into the days and weeks. His health, however, had begun to decline. He underwent heart surgery, a serious intervention that required a significant period of recovery, and that reminded him, if he needed reminding, that the body has its own imperatives that even the most disciplined mind cannot indefinitely override. He emerged from this surgery determined to continue his work for as long as he was able, and indeed he did continue, producing final papers on the non-radial oscillations of stars that demonstrated his undiminished technical powers. These were highly mathematical investigations, concerned with the ways that stars can vibrate and pulsate in modes that depart from simple spherical symmetry, and they represented a return to the stellar astrophysics that had occupied his earliest years as a scientist. Throughout these final years, Lalitha remained his constant companion, as she had been for more than half a century. Their partnership had deepened with the decades, evolving from the early romance of two young people far from home into something quieter and more profound, a mutual devotion that required few words. She managed the practical details of their life together, creating the domestic tranquility that allowed him to focus on his work, and she provided the emotional steadiness that helped him navigate the inevitable disappointments and frustrations of a long career. In the evenings they would sit together, sometimes in conversation, sometimes in companionable silence, two people who had built a life together and who understood each other in ways that went beyond language. Chandrasekhar sometimes reflected, In these final years, on the curious paths that scientific recognition had taken in his own career. The work that had caused him the greatest anguish, his early research on the limiting mass of white dwarf stars, had eventually brought him the greatest honor, the Nobel Prize he received in 1983, more than 50 years after the original discovery. The long decades of being dismissed or ignored, the painful confrontations with Eddington, the years of working in relative obscurity on problems that the wider community did not yet appreciate, all of this had eventually been vindicated, though the vindication had come so late that it felt almost like a message from another era. He did not dwell on bitterness, for that was not his temperament, but he did occasionally express a quiet puzzlement at the way scientific communities could be so slow to recognize fundamental truths. He found solace in the thought that the truths themselves were what mattered, not the recognition they received or failed to receive. A mathematical theorem, once proved, remained true regardless of whether anyone appreciated it, and a physical law, once discovered, governed the behavior of the universe regardless of whether the discoverer was honored or forgotten. This was, for Chandrasekhar, one of the great consolations of scientific work, the sense that one was contributing to something larger and more permanent than any individual career. The equations he had derived, the theorems he had proved, the physical insights he had achieved, these would endure long after all memory of his personal struggles had faded away. His devotion to mathematical elegance remained undiminished to the very end. He continued to believe that the universe, at its deepest levels, was mathematical in character, and that the physicist's task was to discern the mathematical structures that underlay physical phenomena. This belief was not merely methodological but almost metaphysical, a faith in the rationality and beauty of nature that had sustained him through decades of demanding work. When he looked back on his career, he saw a series of encounters with different mathematical structures, each possessing its own character and its own challenges, from the quantum statistics of stellar matter to the curved spacetimes of general relativity. Each encounter had taught him something new about the relationship between mathematics and physical reality. The final months of his life were spent much as the earlier months had been, in reading and thinking and writing, in conversation with Lalitha and with the few close colleagues who remained. He continued to work on the Newton book until it was complete, seeing it through the final stages of publication with the same meticulous attention to detail that had characterized all his work. He seemed to sense that this would be his last contribution, a gift to future generations of physicists who might share his curiosity about the origins of their discipline. The book appeared in 1995, and a few months later, on the 21st of August, Subrahmanyan Chandrasekhar died in Chicago at the age of 84. He left behind a body of work that spanned 6 decades and touched nearly every major area of theoretical astrophysics. More than that, he left behind an example of what a scientific life could be, a life devoted entirely to the pursuit of understanding, conducted with integrity and discipline and an unwavering commitment to truth. His influence on astrophysics was profound and lasting, shaping the way scientists thought about stars and galaxies and the structure of the universe itself. And in his final project, his decade-long engagement with Newton's Principia, he had demonstrated that the love of science, like the love of art or music or literature, was not diminished by age but could deepen and mature, becoming in the end a kind of wisdom. On the morning of August 21st, 1995, in the city of Chicago, where the late summer light falls soft and golden across the lakefront, Subrahmanyan Chandrasekhar passed quietly from this world, his heart having simply grown too weary to continue its steady rhythm. He was 84 years old, and he died as he had lived for so many decades, in the city that had become his home, surrounded by the familiar comforts of a life devoted entirely to the patient unraveling of cosmic mysteries. The cause was heart failure, that gentle surrender of the body's most essential muscle, and though the loss was felt deeply by those who knew him and by the broader community of scientists who had followed his extraordinary career, there was also a sense of completion, of a life's work brought to its natural conclusion, of theorems proven and books written and students guided toward their own discoveries. Memorial services were held in Chicago, where colleagues and former students gathered to speak of the man they had known, his quiet intensity, his unwavering standards, his deep kindness beneath a reserved exterior. There was something fitting about remembering him in that Midwestern city, with its practical character and its long winters, the place where he had spent more than half a century walking to his office, preparing his meticulous lectures, filling notebook after notebook with his careful mathematical script. Another service was held in India, in the country of his birth, where he remained a figure of enormous pride and inspiration despite having spent most of his adult life abroad. The tributes spoke of his scientific achievements, certainly, but they also spoke of his character, his integrity, his refusal to compromise his standards or to seek recognition through anything other than the quality of his work. His wife Lalitha, who had been his companion and supporter through all those decades, survived him by nearly 18 years, passing away in 2013 at the age of 102. Their marriage had been a true partnership, lasting more than 6 decades, and though Lalitha had set aside her own scientific ambitions to support his career, she had been an integral part of his life's work in ways that went far beyond the domestic. She had been his first reader, his thoughtful critic, his steady presence through periods of disappointment and triumph alike. After his death, she worked to preserve his memory and to ensure that his papers and correspondence were properly archived, understanding perhaps better than anyone the historical significance of the work he had left behind. The legacy that Chandrasekhar bequeathed to science is difficult to overstate, though he himself would likely have been uncomfortable with any grand claims made on his behalf. At the center of this legacy stands the Chandrasekhar limit, that elegant mathematical boundary that he had calculated as a young man crossing the Arabian Sea, the threshold of approximately 1.4 solar masses beyond which a white dwarf star cannot support itself against the inexorable pull of its own gravity. This single result, which had caused him such professional difficulty when it was rejected by Sir Arthur Eddington in the 1930s, has proven to be one of the foundational principles of modern astrophysics, essential to our understanding of how stars end their lives and what they leave behind. When a massive star exhausts its nuclear fuel and can no longer generate the outward pressure needed to counterbalance gravity, it collapses upon itself in a catastrophic event we call a supernova, and the nature of the remnant it leaves behind depends critically upon the mass of the collapsing core. If that core is below the Chandrasekhar limit, it may settle into the stable configuration of a white dwarf, but if it exceeds this threshold, no amount of electron degeneracy pressure can halt the collapse, and the star must either become a neutron star, supported by a different and even more extreme form of quantum pressure, or if massive enough, it must collapse entirely into a black hole, from which nothing, not even light itself, can escape. Without the Chandrasekhar limit, we would have no theoretical framework for understanding these exotic objects, no way of predicting which stars would end their days as gently cooling white dwarfs, and which would undergo the violent transformations that seed the universe with heavy elements and leave behind the most extreme objects known to physics. The limit also plays a crucial role in our understanding of a particular type of supernova known as a Type Ia event, which occurs when a white dwarf in a binary system accumulates matter from its companion star until it approaches the Chandrasekhar mass. Because this critical mass is essentially the same for all white dwarfs regardless of their composition or history, these supernovae all explode with very nearly the same intrinsic brightness, making them invaluable as standard candles for measuring cosmic distances. It was through careful observations of Type Ia supernovae in distant galaxies that astronomers in the late 1990s discovered that the expansion of the universe is accelerating, a finding that revealed the existence of dark energy and transformed our understanding of cosmic evolution. This discovery, which earned the Nobel Prize in Physics in 2011, rests upon the theoretical foundation that Chandrasekhar had laid more than 60 years earlier, aboard a ship sailing from Madras to Southampton. In 1999, 4 years after Chandrasekhar's death, the National Aeronautics and Space Administration launched what would become one of the most successful and productive space observatories in history, and they named it in his honor. The Chandra X-ray Observatory was carried into orbit aboard the Space Shuttle Columbia on July 23rd of that year, and it was released into an elliptical orbit that takes it more than a third of the way to the Moon at its highest point, allowing for long, uninterrupted observations of the X-ray universe. The choice of name was deeply appropriate, for X-ray astronomy is intimately concerned with the most energetic and extreme phenomena in the cosmos, precisely the sort of objects whose existence Chandrasekhar's theoretical work had predicted and explained. The Chandra Observatory has gone on to make discoveries that have validated and extended Chandrasekhar's theoretical predictions in ways he could scarcely have imagined during his lifetime. It has observed the X-ray emissions from black holes as they devour matter from their surroundings, revealing the violent processes that occur at the very edge of those gravitational abysses. It has studied neutron stars with their incredibly strong magnetic fields and their surfaces where gravity is so intense that a teaspoon of their material would weigh as much as a mountain on Earth. It has imaged the expanding shells of supernova remnants, tracing the shock waves that propagate through interstellar space and seed new generations of stars with the heavy elements forged in those cataclysmic explosions. In each of these observations, the theoretical framework that Chandrasekhar helped to establish provides the context and the explanatory power that transforms raw data into scientific understanding. Beyond the specific content of his discoveries, Chandrasekhar left behind a model of how scientific research might be conducted, a method of systematic and exhaustive exploration that he applied to one field after another throughout his long career. He would enter a new area of inquiry, master its existing literature, and then spend a decade or more working through every aspect of the problem with mathematical rigor and completeness, publishing a stream of papers that progressively illuminated the subject from every conceivable angle, and then gathering his insights into a comprehensive treatise that would serve as the definitive reference for generations of researchers to come. When he felt that he had exhausted what he could contribute to a particular topic, he would close that chapter of his work and move on to something entirely new, beginning the process again with the same methodical thoroughness. Over the course of his 65-year career, Chandrasekhar published approximately 380 scientific papers, an output that reflects not only his extraordinary productivity but also the breadth of his interests and the depth of his engagement with each subject he pursued. He also wrote 11 books, each one a carefully constructed treatise that brought together his accumulated insights on a particular topic into a coherent and comprehensive whole. These books remain in use today, consulted by researchers who find in them not only specific results but also a model of clarity and rigor that inspires their own work. The students whom Chandrasekhar trained went on to become leading figures in astrophysics in their own right, carrying forward his intellectual legacy and his standards of excellence into new generations. He was known as a demanding teacher, one who expected nothing less than complete mastery of the mathematical and physical foundations of any problem. But he was also generous with his time and deeply invested in the success of those who studied with him. Many of his former students have spoken of the profound influence he had on their approach to science, the way he taught them to pursue a problem with patience and persistence, to value mathematical beauty as a guide to physical truth, and to maintain their integrity even in the face of criticism or neglect. The matter of Sir Arthur Eddington's opposition, which had caused Chandrasekhar such pain in his youth and which had shaped the course of his career in ways both visible and subtle, was largely resolved long before his death, at least in the court of scientific opinion. The theoretical and observational advances of the latter half of the 20th century made it abundantly clear that Chandrasekhar had been correct and that Eddington's objections, whatever their psychological or philosophical motivations, had been wrong. The Nobel Prize in 1983 was a public acknowledgement of this vindication, though it came more than 50 years after the original controversy. Remarkably, Chandrasekhar rarely spoke harshly of Eddington in his later years, preferring to focus on the scientific questions themselves rather than on personal grievances. He seemed to understand that Eddington, for all his failings in this particular instance, had also been a great scientist and a complex human being, and that the advancement of knowledge was more important than the settling of old scores. What remains most inspiring about Chandrasekhar's life, perhaps, is not any single discovery or publication, but rather the model he provided of scientific integrity and dignity under criticism. He demonstrated that it is possible to maintain one's convictions in the face of powerful opposition, to continue working quietly and methodically even when the recognition one deserves is withheld, and to find satisfaction in the work itself rather than in external validation. He believed deeply that mathematical beauty was a reliable guide to physical truth, that equations which possessed a certain elegance and inevitability were more likely to describe reality than those which were merely convenient or ad hoc. This aesthetic sensibility informed all of his work and gave it a unity and coherence that transcended the particular subjects he addressed. The archives of Chandrasekhar's papers, correspondence, and personal materials are preserved at the University of Chicago, where scholars can study the development of his ideas and gain insight into his working methods. These materials reveal a mind of extraordinary discipline and focus, one that approached each problem with the same careful attention, whether it concerned the internal structure of stars or the translation of Sanskrit poetry. They also reveal a human being with hopes and disappointments, with professional friendships and rivalries, with a deep love for his wife and his adopted country and the intellectual traditions that had shaped him. And so the story of Subrahmanyan Chandrasekhar comes to rest, not with any dramatic flourish, but with the quiet satisfaction of a life well lived and a body of work that continues to illuminate our understanding of the universe. The stars that he spent his life studying continue to shine, to evolve, to collapse and explode according to the physical principles he helped to elucidate, and the observatory that bears his name continues to orbit high above the Earth, gathering the X-ray light from distant cosmic sources and sending it back to astronomers who build upon the foundations he laid. In the slow accumulation of knowledge that constitutes the scientific enterprise, his contributions will endure, woven into the fabric of our understanding, long after the details of his personal struggles and triumphs have faded from memory.